conventional sanitary pad. And then we also received 2 different protein foams from the same marine waste recycling company. One had been produced using a conventional protein extraction method, and the other one utilized a more climate-friendly green method. Yes, and here we have the results.
All the results from the absorption capacities were gathered in this diagram right here. And as we can see, the polyurethane form has the highest absorption capacities, while the high concentration slow freezing foam has the lowest. All the other materials come somewhere in between those two. Here we have also the result for the FDIR test. And as we can see on this diagram, all 6 examples that we tested, apart from the polyurethane reference, have reached their characteristic peak at the same spot. This means that they all consist of the same biopolymers. We also calculated the density and gathered them in a diagram. And as you can see in this picture, the high concentration slow freeze styrofoam has the highest density, making it not suitable to use as lightweight absorbent materials. However, if we look at our other materials, they all have a lower density than the polyurethane reference. And finally, we have the pictures taken in SEM test. As you can see that in picture A, B, C, and F, all of them have really large pores, but very thick cell walls. While in picture D and E, they have very much pores, but thinner cell walls. It is also very interesting to note that in both picture A and F, they are actually consisting of the same material. The only difference between them is that they have different concentration of biopolymers. And as you can see on the picture, they get completely different structures. From all the 6 examples we have been tested, 2 of them were selected, and we put them in a patch. And it's surprisingly that the patch is actually really soft, it's very skin-friendly and flexible, and it reminds us a lot like the conventional patch you can buy in the store.
Yeah, so if we compare these two biofoams that were, as Ishu said, produced from the exact same protein solution, the only thing that is different between these 2 samples is the speed at which they were frozen. So the left one was frozen using liquid nitrogen, and the one on the right using a conventional freezer. And the most stark difference is really in the pore size. So if we look at the one to the left, we have a lot smaller pores and a lot more pores than in the one to the right. And this is probably due to how ice crystals form when you freeze a solution. If you freeze a solution very quickly, very, very many small ice crystals form in many different locations. Whereas if you freeze it slowly, you will have fewer water molecules turning to ice crystals at any given time. Which essentially means that you will have a lot fewer ice crystals, but they will be a lot larger in size, creating these large pores. And these 2 solutions were produced in the exact same way, except for that the one on the right had a lot higher concentration of protein. And we can already see that the cell wall thickness of this sample is very thick, and the pores are also a lot larger. They aren't very interconnected. This is something that isn't especially sought after when producing absorbent polymers, as you want the pores to be interconnected to be able to allow liquid to flow through it. So this is also something that you could optimize to get the cell wall thickness you would like and the interconnectedness that you would like to be able to mimic a conventional polyurethane foam. And also, the size of the polymer is very important. As we can see, the sample on the left didn't actually form a biofoam at all. This is due to the low weight and the low size of the protein used. The forces between the protein chains weren't strong enough to form a functional biofoam, whereas on the one on the right had protein chains that were about 100 times longer. And this foam worked really quite well. Yeah, so the conclusion is really that it is quite feasible to produce these sustainable biofoams in an economical fashion that could be used in the industry. And since it's produced from marine waste, it's really supporting circular economy principles and sustainable industrial practices, which is something we want to strive after.
And
Yes.
I would also like to say that for the past 2 weeks we spent in the bio research team, we discovered that this project is about so much more than just science. It's also about sustainability and making our Earth to breathe a little easier. So, and this is something that matters to all of us. So even though biofoams aren't perfect yet, we believe that with improvements and further research, one day it will be possible to replace the plastic-based materials completely.
Yes, and we would like to thank Dr. Antonio J. Capezza for being our mentor during this project, and it's been a really nice time. I would, of course, also like to extend a thank you to all the X-rays that proofread our reports, who have been a huge help.
We would also like to acknowledge Magnus Bergvalls Stiftelse, Jacob Wallenberg Stiftelse, and Särskilda Fonden. Without their sponsorship, this project would not have been possible. Lastly, we would like to thank KTH for providing opportunities for us to carry out this project.
Yes. Now we'll have some time for questions. Yes.
So in your research, you use pretty small samples. Do you think there are any challenges in scaling up? Like when you discovered any differences?
I mean, the production process uses a freeze dryer. So that's really the most challenging element to scale up, since you would need the company, the marine waste recycling company has a more industrial grade freeze dryer. So that's really the most difficult part in scaling up. And that's also the biggest challenge economically. That's the most expensive part of this production process. If we look at the polyurethane foams that are used in sanitary pads, they're produced using extrusion, which is a lot cheaper. But a lot of the industrial processes still use the freeze drying technique, and they're economically viable. So this shouldn't be any issue to get into production. Any more questions? Yeah.
When you say density affects the absorption capacity, do you see any link?
Yeah, that's a bit outside the scope of this study, but there have been links. The biggest correlation is between density and how porous the material is. So if we see that the material has a quite low density, then this would indicate that there's a lot of air. Since it's still the same material, and if the hydrogen porosity is very high, you would have a lot more space where liquid could be absorbed, generally indicating a higher absorption capacity. But of course, if you have a porosity of about 99%, you will have some structural challenges, right? And perhaps you will have issues with the solubility. And yes, so it's all a balancing act, really.
Yeah, and as you can see on this diagram, you can also see that low concentration native SF have really low density. And as we can see the result in SEM, they have a very poor structure. And this is also the reason why they have like really low density, because they have so much force.
Yeah, so that's absolutely something to be investigated further. And again, this is all really about optimizing the production of these biopolymers to be able to create a sustainable solution to this problem. Well, thank you.
Thank you, Simon and Yishu. Now we have the next presentation. Let's see. We want to welcome up Anisa Jafari. Anisa is entering her third year of the Natural Sciences program at Södra Latins Gymnasium. She has a strong interest in neurobiology and in how biology and computer science can be combined in better understanding and treat disease. Anisa enjoys creative problem solving, especially through programming, and is proficient in several languages. And she has also achieved excellent scores in mathematics competitions. At Karolinska Institutet, she has worked under the guidance of her mentor, Giada Di Nunzio. welcome up Anisa. So, hello everyone, welcome to my presentation. My name is Anisa Jafari, and my project was about the role of Kupffer cells in atherosclerotic plaque development and stability in apoE knockout mice. So let's start with a major global health problem, metabolic syndrome and its hepatic manifestation, MASLD. Metabolic syndrome is a cluster of metabolic disturbances including obesity, insulin resistance, hypertension, and dyslipidemia. So metabolic syndrome is becoming increasingly prevalent in our modern societies due to our modern lifestyles, such as lack of physical activity and our poor dietary habits. Metabolic syndrome often leads to MASLD, or for a condition formerly known as non-alcoholic fatty liver disease, which is the most chronic liver disease worldwide. It is the pathological accumulation of lipids in the hepatocytes. Crucially, both metabolic syndrome and MASLD impair the body's ability to process fatty lipids, which increases the risk of cardiovascular disease. Cardiovascular disease is another big health challenge globally, affecting over 500 million people, and is the leading cause of the mortality worldwide. So, while MASLD is a liver disease, the primary cause of death in patients with MASLD is cardiovascular disease. So this raises a critical question: do they share a common underlying mechanism? One key candidate is the disrupted lipid metabolism that can set the stage for atherosclerosis. And atherosclerosis is the core problem of cardiovascular diseases. So now let me briefly walk you through what atherosclerosis is. So atherosclerosis is a chronic inflammatory disease that starts when fatty plaques build up inside your arteries. So we have LDL particles, or bad cholesterol, that get stuck and oxidize in the endothelial layer of your arteries, and then this triggers an inflammatory response that recruits monocytes. The monocytes are immune cells that recruits monocytes to that site, and these monocytes differentiate into macrophages, and these macrophages can engulf the lipid particles, becoming foam cells. Simultaneously, vascular muscle cells can migrate into the intima to form a protective fibrous cap to contain and stabilize the plaque. So over time, when the plaque matures, this fibrous cap becomes thinner, and the plaque becomes more vulnerable, which makes it more prone to rupture. And when the plaque ruptures, it can cause critical cardiovascular events such as myocardial infarction and strokes. So now, where do Kupffer cells come into this picture? So Kupffer cells are the liver's resident macrophages. Under normal pathological conditions, they help regulate lipid levels and maintain immune balance. But in conditions such as MASLD or metabolic syndrome, these Kupffer cells accumulate excessive cholesterol, and they become also foamy cells. And this can trigger an inflammatory response, and they become pro-inflammatory.
And this pro-inflammatory response results in increased secretion of cytokines and the recruitment of monocytes, which can potentially lead to smooth muscle cell activation and remodeling in the arteries. So this brings us to the central aim of the study. The central aim of the study was to investigate how depletion of copper cells influences the atherosclerotic plaque architecture in a setting of metabolic dysfunction. To investigate this, we used this model on a pre-knockout mice, which can naturally develop atherosclerosis. So to selectively deplete copper cells in these mice, we introduced a pre-recombinase system that is driven by copper cell specific PLEC4F promoter. And then we crossed these mice with another line that expressed human-like inducible diphtheria toxin receptor. And then when these mice are crossed, only copper cells start expressing this receptor. So when we injected diphtheria toxin in these mice, these copper cells were depleted, giving us a clean model to study their role. We included two groups of mice in our study: an experimental group whose copper cells had the diphtheria toxin receptor, and a control group whose copper cells lacked diphtheria toxin receptor. But both groups received diphtheria toxin injection 2 weeks, twice per week for 8 weeks, and it continued until the age of 18 weeks. At the age of 18, mice were euthanized via carbon dioxide, and we collected their hearts for further analysis. So this is my methodology. We focused on the aortic route, but I'm not going into too much details here. So we focused on the aortic route, which is a common site for plaque formation. And then we used immunohistochemistry to analyze the plaque formation composition. There were two main markers that we used for the staining method. The first one was alpha smooth muscle actin, or alpha SMA, that was used to detect smooth muscle cells in the aortic route. And the second one was CD68 for detecting macrophages. And here we see a representative smooth muscle stained advanced atherosclerotic lesion in a knockout mice. So here smooth muscle cells are stained magenta, and the nuclei are stained blue. And in this figure, we can see typical features of an advanced atherosclerotic plaque. We see an necrotic core that almost lacks nuclei, and then we see a well-developed fibrous gap. Here we see a dense immune cell infiltration. So this is how a plaque should look like. And then before our main analysis, to confirm the actual plaque regions in our further studies, we used oil red O staining method to localize the plaques, and these red stainings are the lipid-rich plaques that we were studying. So next slide, we can see the same plaques, but with smooth muscle staining. So to compare the results from the groups, we see in copper cell mice there is a well-developed fibrous gap, as it is stained with magenta color, and we see that nuclei are arranged in a somehow organized pattern, but in the medial layer there is minimal staining. Whereas in the copper cell depleted mice, we have a thick and prominent medial layer of smooth muscle cells, and we have almost no smooth muscle cell expression in the fibrous gap. So this means that the smooth muscle expression in the copper cell depleted mice were minimal. And here, to evaluate the macrophage infiltration level between the two groups, we did immunohistochemistry with CD68. And here we can see the results. In cover cell positive mice, we also see a dense macrophage accumulation in the plaque core, but we see the same results in cover cell depleted mouse as well. So we can say that the results are comparable because there is no visible staining, there is no visible differences in these two figures. Now the discussion part. So to conclude our studies, we demonstrated that cover cells alter the overall architecture of atherosclerotic plaques. Yes, and more specifically, we observed a reduction in smooth muscle cell expression in the atherosclerotic plaques in the fiber stems specifically, and which resulted in thinner caps. And this thinner cap could imply a more vulnerable plaque that is more prone to rupture, which is exactly the reason of heart attacks and strokes. And for the macrophage staining, we didn't observe any noticeable difference between them. So this means that despite the structural differences, the macrophage infiltration level was the same. Yeah. And then, although cholesterol levels were not measured in this study, further previous work from the same laboratory has shown that cholesterol levels were not changed after cover cell depletion, meaning that these observed changes were unlikely to be driven by cholesterol. And that means that there could be signals deriving from cover cells from the liver that could circulate and influence the vascular remodeling. Yes. So to summarize, our overall conclusion is that cover cells could be potential regulators of atherosclerotic plaque stability, and that cover cell resulted in cover cell depletion resulted in specifically thinner fibrous caps. That means a plaque is more prone to rupture, and the plaque is more vulnerable. And so, looking ahead, the next step of our study could be to identify the liver-derived signals that cover cells could secrete from the liver from distance to affect these plaques in the vascular. This understanding this pathway could position cover cells as a new therapeutic target in cardiovascular disease. So now I want to express my deepest gratitude to my mentor, Dr. Tiden at Karolinska Institute for her generous support and for her patience, as well as her guidance that inspired me during this whole 2 weeks period of mentorship. And I'd also like to thank organizers of this year's RACE program for their inspiring lectures and also for their dedicated participation. And this project was generously supported by AstraZeneca, Stiftelsen Reinhold och Einar Nordströms minne, Jakob Wallenberg stiftelse och Särskilda fonden. Thank you very much.
How easy are copper cells to actually target in practice in humans? But because for this experiment, we had to specifically breed mice in order to have copper cells that are easily exterminated.
Yeah. So I mean, these mice were endpoint knockout mice, which means that they are prone to develop atherosclerosis, and because natural wild type mice, they cannot develop atherosclerosis because they must have their cholesterol level in HDL, which cannot develop plaques. So we had to use transgenic mice, and this is mostly to study. I mean, they are a model that their lifespan is short, so we can study them quite fast, and they're also quite human-like, so we can compare them to atherosclerotic plaque development in humans as well.
What is the main difference between Kupffer cells and like macrophages? Regular members?
Well, Kupffer cells are the liver's resident macrophages. So we have like different different macrophages in the innate immune system in the body, and we also have a adaptive immune system. But like the macrophages that we observed in our results, they were like from innate immune system. But Kupffer cells, yeah, they're like liver's macrophages. They kind of like circulate around them. Yeah.
Your presentation was really interesting, and correct me if I'm wrong, but you used both male and female mice?
In this study, we use female mice,
Yeah,
because they develop bigger plaques.
Yeah, because that was just what I was wondering, if you notice any big difference with using female mice.
Well, yes, in female mice, we noticed bigger plaques. I mean, I think that there is a genetic background behind it, but in humans, it is different. In humans, we observe a bigger plaque development in males compared to females. Yes. Yeah. Thank you.
Yes, thank you, Anissa, for that very interesting presentation. So next up, we want to welcome Dante Wigren and Henrik Waldeck. Dante is currently studying the natural science program at the Gymnasiet in Örebro. He has especially an interest in mathematics, computer science, modeling, and simulation. Aside of academics, Dante is also running a UF company and is actively involved in sport, both as a basketball player and as a coach in both basketball and fencing. Henrik studies the physics specialization program at Polhemskolan in Lund. His passion for science has grown through participation in numerous science camps and programs, both as an organizer and as a student. He has also competed successfully in the Astronomy Olympiad, and to share his interest with others, he founded GLARE, an astronomy club in Lund. Besides science, he has also taken on a strong interest in music. During their research project at KTH, Dante and Henrik have worked together under the mentorship of Raquel Lizarraga Jurado. Give them a warm applause.
Is it working? Ooh. Hello? Oh. Yes, thank you, Selma, for the introduction. I'm Dante Wigren, and this is Henrik Waldeck, and welcome to our presentation on how we use quantum mechanical simulations to design sustainable batteries. Let's talk about lithium batteries. We all know them, we all use them. They're everywhere in today's society, in every electrical device. As the modern technology advances, the demand has skyrocketed and is projected to grow 27% annually until 2030. But although the extensive use and limitless possibilities, there are some setbacks, serious setbacks. For example, the production is not sustainable or ethical, and new solutions are desperately needed. Among the problems with lithium batteries, one of them is environmental problems. For example, extracting lithium is extremely water consuming, and up to 1900 cubic meters of water is used to extract 1 metric ton of lithium.
Also, plating and dendrites are a problem in lithium batteries and can cause short circuits or even thermal runaway, which may lead to an ignition or explosion inside of the battery. And these problems mainly occur due to the electrolyte in lithium batteries being a fluid. An alternative is solid-state batteries, which use a solid glass-like structure as electrolytes. And therefore, the aim of this study was to use quantum mechanical modeling to replace lithium in lithium batteries, and to decide good solid electrolytes.
So, if we were here to explain quantum mechanics, we would probably be here like until tonight. So you have to trust me that quantum mechanics is a deep and like really complicated field that describes how particles behave on the smallest scales in our universe. But we also now, due to our project being about quantum mechanics, we want to simulate all these particles and all these interactions in a chemical structure. Therefore, we have to in some way compute these complicated interactions. So we have to do some simplifications and some workarounds to be able to do these calculations. The first one of which is using ionic cores or also pseudopotentials. Because an atom consists of a nucleus with surrounding electrons. And it's the valence electrons, the electrons on the outside of the atom, that are most involved in chemical bonds in the structure. But this means that if we have to simulate all these electrons and all these interactions, we are basically wasting so much time and so much computation on the innermost electrons. These electrons, the core electrons, are basically redundant in our simulations. Therefore, we can, in a sense, disregard them. Because if we were to have all of these atoms in a structure, we would waste so much time and the complexity, and it would be practically solved. So instead, we see the whole core with its core electrons as an entire particle on its own, a quasi-particle, which has its valence electrons. So we now have, instead of a nucleus with the core electrons and valence electrons, we just have an ionic core with valence electrons. So fewer electrons, fewer particles to simulate.
Thank you. Another way to facilitate the process is to use the model called density functional theory, or DFT. And the underlying theory is that the properties of a quantum system can be described by the electron density. So instead of calculating all interactions between all individual electrons, you calculate the interactions between one electron and the rest. So it's sort of like an electron cloud. And a program you can use to simulate these materials is Quantum Espresso, where you take input files and commands and design the material structure you want to simulate. And there are a couple of steps used when you want to simulate the properties of a material to determine if it's a good electrolyte. And the 3 steps are to find a reasonable accuracy, the optimal lattice structure, and the insulation properties.
Yes, and as Dante was saying, we first have to find a reasonable accuracy, because it turns out that an accurate simulation, a precise simulation, isn't equal to a fast simulation. They don't go hand in hand. So therefore, we have to find the optimal amount of inaccuracies we can allow in these simulations without having to use as much time. So if we look at this graph here, we can see that we need to find the shortest possible simulation time, or the shortest amount of accuracy with the least amount of accuracy we need to find to get an accurate result. Because we're going to run these simulations for plenty of iterations, almost 100 iterations, and spending too much time on one simulation means that we have to spend less time on others. And our goal with this project is to search through as many combinations and as many structures as possible. So by using too much computation time, we are basically limiting our scope of this study. Next up, when we found a reasonable accuracy of the simulation, we want to find the optimal structure of a material. This is done by, when we have our structure, we can either elongate it or move the atoms about the structure, or compress them together. This yields we have the total energy stored in the system, which can be viewed as the chemical energy stored in the structure. We want to find the structure with the least amount of energy, the most stable structure. So it's a problem of minimization. We want to find a minimum of all the possible combinations, which is a pretty big task to do, but with plenty of simulations and quick ones, we can do it iterate through a lot of conditions. When we found a good structure, an optimal structure, it's time to search through and determine the insulation properties of the material. This is done by plotting the electron abundance over the energy an electron has. So we're basically looking at the electron clouds, or the possible places electrons can be in the electron cloud around an atom, or the amount of structure. So we have two bands that, if they are connected, the valence band where all the electrons are contained, and the conductive band where they can conduct electricity. If they are connected by the third level, this means that electrons in the valence band can, when forced by voltage or energy, they can jump over into the conductive band and start conducting electricity. This is a bad electrolyte because it conducts electricity. The electrolyte lies between the positive electrode and the negative electrode. If it were conductive, that would mean the battery would explode. So bad. So therefore, we want to separate the conductive band from the valence band as much as possible to ensure that we have a good insulator.
For the method used, we're going to use copper as an example material to demonstrate the procedure and what we did. So first, as Henrik mentioned, we simulated copper a couple of different times and plotted the total energies for each accuracy to find where the value had converged and use the value for the rest of the simulations. Next, with the accuracy, we did some more simulations and plotted the total energy based on the distance between the atoms in the structure. And we plotted the results into a graph and found the minimum value where the material was the most stable. And here is the structure visualized we used for the last simulation, where we plotted the density of states, or as Henrik mentioned, the bands. And as you can see here, the bands are in direct contact with each other, which means that electrons can move freely across, making it a bad electrolyte, which is reasonable because it's copper, it's a conductor, so it's what we expected.
So, for the results, we started with a electrolyte that has been proven to be a good candidate for solid electrolytes, which is lithium chlorate, which is something Raquel here in our stage has been studying, because it's a good candidate. And as we can see here, it has a band gap of around 5 electron volts. If we then we did we tried to what happens if we would replace all the lithium with, for example, sodium, which is the element below lithium in the periodic table. And the result we got then was a significantly lower band gap, but a still significant difference in, or a significant difference in the levels of the valence bands and the conductive bands. Thus, we actually found a semi-working candidate, but we wanted to improve it. So our next assumption or our next guess was something like that. Sure.
Yeah, as mentioned in the beginning, we don't like lithium. It's bad for the environment, and we don't want to use it. So we tried sodium. It worked, but it wasn't as effective. So we thought, okay, what if we take one of the lithium structures and place it next to one of the sodium structures, and created a hypothetical material which hasn't been studied earlier. So we have no expected values, but since we're taking 2 insulators, we thought that we would get an insulator. And it was correct. We got a band gap of 2.49 electron volts, which it's wider than the only sodium. It's not as big as just lithium, but it's an improvement, and we're using less lithium, which is bad for environment, so it's a step forward. And yeah, as we compare the band gaps between the materials, it's clear that lithium is the most effective, but combining it with sodium does improve the effectiveness while reducing the amount of lithium.
Yeah, and as we tested the structure that has actually been more thoroughly simulated and almost also experimentally reproduced physically, we can see that our simulated values, at least for the lithium fluoride, are within like a reasonable margin of error. We are like around 1% of error here, which means that our method is a pretty good benchmark of real-world properties. But we have an outlier, which is sodium chlorate, which can be due to a lot of unexpected differences when selecting, for example, the accuracy of simulation. But within we can at least say that we're in within 20% of the correct amount, which is still really, really good. So in this study, we were able to distinguish from insulators and conductors to be able to find good candidates for electrolytes. We got reasonable results compared to real-world examples, and we can now use this as a benchmark to be able to look through a lot of materials to see if they are good candidates for electrolytes. So essentially, we have proven that our method is viable in searching for electrolytes.
Yeah, so the conclusion, as Henrik mentioned, we got reasonable results that indicate the reliability of quantum mechanical simulations and using it as a method for finding new electrolyte candidates for batteries. And lastly, we just wanted to thank Raquel, our mentor, for helping us throughout this project. Also Tekniska Museet and Stiftelsen Lars Minne for making the race possible. And lastly, the Race for Excellence, our organizers, our colleagues, thank you for this amazing experience. And now we're open for questions.
Yeah. So the structure of the lattice itself, how much control do you have over that? Because is it like determined by the chemistry of the atoms, or is it something that you can control as like an additional variable? Because I imagine the structure will also affect the interaction between the atoms.
Yeah, we can simulate like any arbitrary structure. We can choose any possible structure and see how much energy it contains.
Right.
Therefore, we can essentially make up new materials, invent completely new materials that wouldn't be physically possible. But we can still analyze them.
Yeah.
Would they be good candidates?
So I have a question regarding, do you know why lithium is better than sodium?
Well, I would guess that it's based on the size of the atoms, due to lithium being it has three nucleons. It's pretty lightweight. Sodium being a lot bigger, that could in a sense affect the result. But actually, that's something that could be further studied because I'm not sure. That's a good question.
Do you have any suspicions of how possible your new lithium and sodium mix would be to actually create?
Just to begin, the simulations we are doing, it's not like the whole process to find new electrolytes. We have tried the conductivity and the insulation properties of the materials. So just because they can conduct or doesn't conduct electricity doesn't make it a good electrolyte.
Yeah. There are more complicated processes in finding good electrolytes. This is a process that takes 5 years, for example. But the next steps are, for example, there's no property of electrolytes that are really important to get right, and that is that the structure has to be able to conduct ions as well. So it should be able to conduct ions, which are large charged particles, but not electrons, which are small charged particles. So that's a more complicated analysis to be done. But by doing these simulations, like before the other ones, we can more quickly sort out which alternatives are even viable to begin with. So in a sense, it's important to be able to, we have a benchmark here, which candidates are possible, and then we can sort out examples that would be like viable in any sense.
And can you actually find out whether or not these materials can conduct ions with the program you used?
I believe so, or at least in other computational programs, because it isn't the problem now that calculation faces is that we have to now consider for these like large ions to be able to pass through. So we begin to have a mechanical problem as well upon this quantum mechanical problem. So it can be done, and that's why we're trying to find options through this method first instead of doing it the other way around, because those calculations take much more time and much more effort into them. So by sorting these alternatives first, we can sort out the ones that are good. Question up there.
How long does it take to analyze?
Well, if we go back to the copper one, we got these simulations to run for like 10 seconds, that's quick. But for the more intricate structures, sadly enough, this process took, for example, 4 hours, I believe. But that's on a personal computer. This can be done on like a mouse scale, on a supercomputer or like a server rack. So therefore, even though it's a intricate simulation software and a lot of processes that have to be handled, we can still with pretty average computer analyze a lot of complicated materials without having to use, as I said, supercomputers. So the these applications we talked about, even though they introduce some errors, as we saw with as saw here, it can still be said that we get a sort of accurate result in a time span that's for example, with copper, 10 seconds. That's insane.
Yeah, thank you.
Thank you, Dante and Henrik, for this presentation. Now we will take a 10-minute break because we're a bit too fast. So we need to take a few moments and we will start again at 11:15 for the next presentation.
förebyggande.
Jo, exakt. Koncept.
Har du varit mycket om Reese som behind the scenes? Eller?
Ja, det är syrran som
ja, exakt.
Så jag lite har jag
Ja, det är nice. Gick det nu eller var det close?
Nej, jag var där. Alltså, det var lite så här Q&A. Det så jag fick svara liksom, hur är det för att få på?
Ja, kul.
Ja, nej, det.
Ja!
Men har du varit på race innan? Eller så?
Ja, jag arrangerade förra året.
Okej, förra året.
Och jag var elevprojekt. Men det kan bara värva fler och fler som i alla fall kanske två från Eleverna när jag var arrangör.
Ja, en trevlig process. Kommer tillbaka.
Det är exakt samma för.
Ni kan inte göra det. Vi ser inte jätteentusiastiska ut.
Här var väldigt ställningar. Också premiumsvänner. Och Erik. Han var det. Det är alltid kul. Först en dag, eller en kväll. Så att jag och började jag var inte så och sen bestämde jag 3 timmar för fysik. Ingen av oss fick upp efter fysik.
Det andra om levergrejen. Jag hänger lite vad som resultat är. Jag fattar inte riktigt vad ja, så det där är inget jag ska inte läsa.
Har du koll på arbetsarbetet?
Ja, därför jag ska vara lyssna.
Yes.
Jag kommer tro det. Alltså, en öppna musik. Ja, men det kommer en biolog.
Det är en förbättring, så jag tar den. Jag kommer inte lösa projektet på ett annat sätt. Jag gissar att det kommer bli ganska kommer du klara av det? Ja, det sitter jättefint. Okej. Jag tror att det kommer till det är snart liksom allt så här.
Jag sa bara...
Fast det är inte heller särskilt bra, vi säger. I längden kräver kroppen sömn.
Ja, då så är det vaken eller 12 timmar sömn. Ja, mer sömn är ändå så här från ja, men jag är upp på
standard av vilken som är det.
Det är antingen här. Jag är på 2 ändar någonstans. Ja, jag är bara fantastisk. Vad blir det för dig?
Vad ska du plugga?
Skolan heter
Jag missade piken där. Vi får se. Som man har. Ja, det är inte så. Jag hoppas att någon är där i alla fall. Jag ska göra en Yes. I Uppsala har det inte 22,5 i antagning. Man säger bara det va? Nej, jag vet inte. Jag kommer ändå inte. Så är svårt. Vad är hårt?
Great, welcome back everyone. Now we'll continue with the presentations, and next up is Anastasia Saracina. Anastasia is enrolled in the IB program at Tekniska Museet in Gothenburg. She's highly accomplished in competitive programming and mathematics, with several international Olympian medals to her name, including gold at the European Girls' Olympiad in informatics. In addition to competing, Anastasia also lectures at programming camps, sharing her expertise with others. At KTH, she's worked under the guidance of mentor Kai Munoz Arvidsson. Welcome up, Anastasia.
Okay. Yeah, I think it works now. Thank you, Hannah, for this introduction. So, autonomous systems, such as self-driving cars or food delivery drones, become more and more present in daily life. To enable the usage of many of them in the same environments, safety analysis is essential. By safety, we mean guaranteeing the avoidance of all physical obstacles while staying in the range of safe conditions. To ensure that an obstacle can be avoided, we need to consider all trajectories a system can take. This can formally be done by, for example, Hamilton-Jacobi reachability analysis, which was the focus of this work. However, the main challenge with this is the fact that it suffers from curse of dimensionality, and as the number of state dimension increases, the computational time becomes too high for it to be practically used. The main contribution of my project would be to decrease the computational time by introducing a narrow banding technique. So a state of a system is described by several state variables, such as, for example, position, velocity, or angle, and it evolves with time depending on two factors. First is control, which demonstrates how we control the system, for example, changing the wheel's direction or accelerating the vehicle, and disturbance, which refers to how the external influence changes the parameters. Together, control and disturbance determine the trajectory a system takes. There are several types of reachable sets we may want to compute to analyze safety. First one is the minimal backwards reachable set, which includes the states for which all trajectories lead into the danger. Another one is the maximal backwards reachable set, where at least one trajectory leads into the target set, which in this case is usually the goal region. Even though there exists many other types of reachable sets, the computation principles for all of them are similar. And in this work, we will specifically focus on computing the maximal backwards reachable set. Hamilton-Jacobi reachability introduces the value function to describe how safe or how desirable the state of a system is. In case of the maximal backwards reachable set, the states that have a non-positive value function are inside of the representation of the reachable set. So they are desirable in this case, since we can get to the target region from those states. Initially, the value function is the signed distance to the border of the target set. It then evolves with time according to the optimal control and worst case disturbance. In my work, I used the existing OptimizeDB toolbox to numerically compute the reachable sets by representing the entire state space in a grid. The algorithm used in this toolbox has two main stages. The Hamiltonian stage which computes the Hamiltonian that shows how the value function changes. It depends on the system dynamics and the current value function gradient. And also the dissipation stage, which smooths out the Hamiltonian, and it satisfies the so-called CFL condition, which limits the velocity of value function's propagation to only one cell per time step. This decreases the numerical errors. These two iterations are repeated until the entire time horizon is covered. The main idea behind the narrow banding method is to decrease the number of states we update at each iteration instead of updating the entire state space, only focus on the states around the border of the target set, the border of the backwards reachable set. To do this, we introduce two sets. It is the immediately updated set, which includes states for which the value function's absolute value is lower than a threshold value beta. And the potentially updated set includes the states around that region that can enter the immediately updated set at the next iteration. Whether a state in the potentially updated set should be updated is determined by the intermediate value function of its neighboring states that have already been calculated. The value function, the value of beta has to be chosen depending on the grid resolution, since the CFL condition in the dissipation stage limits the value function propagation by only one cell per time step. Too low values of beta might lead to the border of the reachable set escaping the beta region, and therefore beta should be chosen as at least the numerical range of the states 2 cells away. We have conducted several numerical simulations to evaluate both accuracy and the time performance of the narrow-banded approach. In all the simulations, we used the 2D double integrated model that has states that are determined by the position and velocity in both axes, where the control determines the acceleration and disturbance affects all state variables. First of all, we wanted to visually compare the computed value function with and without the narrow banding approach. We present here the slice of the value function for fixed velocities in both axes, and with red we have highlighted the boundary of the reachable set. Additionally, we present the zero level set, which represents the entire maximal backwards reachable set on the state space for position in both axes. We additionally present a slice of the value function for fixed position and velocity in y-axis, and as we can see in both cases, the computed backwards reachable sets look identical visually. But to further evaluate this similarity, we have calculated the intersection over union between the computed zero level sets for the two methods. We've done this calculation for different time horizons and varying beta factors. Since in safety analysis applications we are typically interested in low time horizons, we have tested it here from 1 to 3 seconds. And also the beta factor, as stated before, should be at least 2. So beta factor refers to the number of consecutive states, which numerical range we assign the beta to. And as stated before, it should be at least 2. However, higher beta factors would result in better accuracy. We have also compared the running time of the narrow-banded method with existing approach. The key factor that affects the relative time of the narrow-banding technique is the proportion of states that we update at each iteration. One of the factors affecting this would be the size of the target set. And for these computations, we have changed the target set sizes and compared the time. As we can see for the smallest target size, the narrow banding decreased the computational time by 87%. Another factor affecting the time is the grid resolution. Since we fixed the beta factor at 2, the higher grid resolution will result in a lower proportion of states covered by the beta region. This can be seen here, since the relative time by the narrowbanding algorithm decreases with increasing cell resolution. The narrowbanding approach, of course, introduces several approximations. First of all, the gradient of the value function may be under-approximated for states at the border of the updated set, since their neighboring states might be outside of those we update, and they would hold the threshold value of beta instead of their true value function, which would have a greater magnitude. In this case, the gradient will be under-approximated. However, in the grids with high resolution, this error wouldn't be that significant because the value function changes gradually from one state to another. Another source of error lies in the fact that the intermediate value function calculated for states in the immediately updated set does not account for dissipation coefficient in states in P, which results in perhaps incomplete information when making a choice about which states in P to update. But as we saw before on the accuracy evaluation with the intersection over union, for low time horizons, this also doesn't affect the accuracy that much. While narrowbanding technique decreases the computational time, the memory still remains the same, since the entire state space is stored. Future research might focus on decreasing the memory usage of this algorithm by using the specified grids, or keeping only the value function of the states around the border of the reachable set instead of the entire grid. And also it might be interested in combining the narrowbanding technique with other approaches such as system decomposition. To conclude, I would like to say that the intersection over union remains higher than 95% for low time horizon and lower band beta factor, which is very accurate in this scenario. Visually, the results, so the computed backwards reachable set also look same. The time is decreased by 87% for small target sizes, and the time improvement factor continues to increase with increasing grid resolutions. This makes the narrowbanding approach makes Hamilton-Jacobi reachability closer to being used in practice by mitigating the curse of dimensionality. I would like to thank my mentor, Kai Munoz Alfredson, for guiding me throughout this project. It was great working with you, and I will never forget this experience. I would also like to thank previous year's RACE participants for reading my reports and providing valuable feedback. And I also want to express my gratitude to the Research Academy for Young Scientists, Tekniska Museet, and Tagesvans Stiftelse för undervisning och forskning for making this possible. Thank you.
Yes. I don't know if you addressed this, but is there a possibility that narrowbanding can have accumulations of error over time? Because even error of like 95% over many iterations, I mean, steps could accumulate. Or
yeah, that is true. And as we saw on the, as we can see on this graph where we present the heat map of the accuracy or intersection over union for different time horizons, the error increases with increasing time. However, in the applications of safety analysis, we are usually interested in low time horizon because we want to either avoid an obstacle fast, and we are usually interested in such computations.
Yes.
Any more questions? Yes?
Did you look at adding stochastic disturbances? I don't know if I caught that in any of the formulas.
Sorry?
Disturbances. Do you add? Was there any randomness involved? Like to model, for instance, outside interference?
Yeah. In the 2D double integrator model, the disturbance affects all system variables. So yeah, it was included. Thank you.
Yes, thank you very much for that presentation. Next up, we'd like to welcome Eugene Yang and Gabriel Textorius to the stage. Eugene is currently enrolled in the IB program at Katedralskolan in Lund. He has a strong passion for theoretical physics, particularly in the areas of general relativity, quantum field theory, quantum mechanics, and string theory. Eugene has independently conducted several research projects and has achieved excellent results in national science competitions. In her free time, she enjoys reading, digital art, and badminton. Gabriel studies the science program at Europaskolan in Strängnäs, where he nurtures his interest in mathematics through university-level math courses in collaboration with Stockholm University. His love for problem solving has led him to participate successfully in several scientific competitions. Outside of the classroom, Gabriel has practiced karate for many years and enjoys spending time in nature. And now let's give a warm applause for Eugene and Gabriel.
Hello, yes.
Hello. Oh, yep.
Yeah, thank you, Selma, for the introduction. Yes. My name is Gabriel, as heard, and I'm studying automagnetism.
My name is Eugene, and I'm going to talk about topological spin structures.
Yes, magnetism. But before we start, I want to thank our mentors, Jasmin Sassa and Martin Månsson, for guiding us through this project.
It's been a wonderful experience working with you. And then we'd like to thank our collaboration partners.
Yes, first of all, Europaskolan Stiftelsen. Europaskolan Strängnäs has been our base of operation these last 4 weeks.
And then we'd like to thank Jakob Wallenberg Stiftelse for giving us money to fund us.
Yes. Well, first of all, magnetism is something that's very important in our society for technology. It's in our mobile phones, our credit cards, and in a bunch of other sorts of technologies. However, there are some applications that require new magnetic phenomena to be fully understood to use them. And that's what we've been studying.
All right, first of all, I'd like to explain a concept that is central to both our projects. What causes magnetization? The reason materials respond to external magnetic field is because each electron within the material has something called a magnetic moment. Think of the moment as a vector pointing from the south to north pole of the presumably spherical electron. This moment has a tendency to align with an external magnetic field, much like a compass needle does. But what puzzled physicists for years was how this moment arose in electrons in the first place. They try to explain it by thinking of the electron as a uniformly charged sphere spinning on its axis, which is why this property is also called spin. However, their explanation was wrong, so they just thought of spin as a quantum number and moved on with life. And that is the explanation we should stick with.
Yes, it's important to understand the three main types of magnetism. First one is paramagnetism. In a paramagnet, all the magnetic moments in the material are ordered randomly. Or in other words, there is no order at all. However, if you apply an external magnetic field to a paramagnetic material, the moments align with the field and contribute to it and makes it stronger. In a ferromagnet, the moments are already aligned spontaneously, meaning that they generate their own magnetic field. And this is usually when you think of your everyday permanent magnets, those are ferromagnets. We also have anti-ferromagnets, which have ordered moments, but the moments are ordered in such a way as to they all cancel each other out. There's no generated magnetic field. It still retains some useful magnetic properties that can be used in some applications. The one important thing to measure about magnetic materials are their susceptibility, which is a measure of how much they contribute to an externally applied magnetic field. The susceptibility is proportional to the applied field, it's usually temperature dependent. And you see for the different materials, the graphs for temperature looks different. But usually susceptibility is decreasing with increased temperature.
Previously, we mentioned that the spins in a ferromagnet spontaneously align even in the absence of external field. Thermal fluctuations, however, destroy this alignment because higher temperatures make the spin orientations more random. The decrease in magnetization with increase of temperature can be described in Bloch's law, which is this formula over here. So M bracket T is the magnetization and temperature T, V is the volume of the material, and all this mess before T to the power 3/2 are just numerical constants. And please keep this formula in mind because we'll use it later.
Yes, the focus of my study has been on a fourth magnetic state called ultramagnetism. And superficially, ultramagnets look quite a bit like antiferromagnets because all the spins are aligned to cancel each other out. But to understand the difference between an ultramagnet and an antiferromagnet, we need to look at something called spin splitting. Spin splitting essentially means that the energy required for an electron to have spin up or spin down is different. In a regular ferromagnet, you see that the energy for one spin direction, for example, spin up, is always lower than the energy required to have spin down, which is why most moments are pointing spin up because that requires less energy. In an antiferromagnet, there isn't a spin splitting, which basically means that there's no energy difference between having a spin up or spin down, which are around half a spin up, half a spin down, and they all cancel each other out. In an antiferromagnet, there is a spin splitting. However, it's not uniform. For different electrons, some electrons will have spin down require less energy, but others will have spin up require less energy, which means there's still a 50-50 split between spin up and spin down. There's still an energy difference in which spin direction a specific electron can have, which gives you some useful applications in technology without having the stray magnetic fields that ferromagnets have, which can disrupt nearby electronic devices. The ultramagnetic material I'm studying specifically is chromium antimonide. You can see this crystal structure right here. One thing to kind of keep in mind when you're working with sort of materials are the effective magnetic moment of the atoms involved. So basically how much that atom contributes to the magnetic field. And that can be calculated using this formula here, where n is the number of unpaired electrons of the ion. And calculating that for chromium ions, we get a value of around 3.87 for magnetons. However, this model does not take into account the interactions between particles, and so it is not always strictly followed.
As an introduction to my project, I'd like to talk about topological spin structures. Topological spin structures are like vortices of spin that form in materials with a type of twisting interaction called DMI, or the Joyaloshinsky-Moria interaction. And here are some examples of what they look like. No, laser pointer, but okay. These structures are characterized by something called the winding number. So if you take all the spins in the structure and place your ends at the center of a sphere, the number of times their heads wrap around the surface of the sphere is the winding number. And there's this beautiful math theorem that says that the winding number stays unchanged under smooth deformations of the spin structure and can only take on integer values if two criteria are met. The first of which is that the spin field is continuous and smooth, and the second of which is that the spins at the boundary of the spin structure are uniformly polarized. And by uniformly polarized, I just mean that all the spins at the boundary point in the same direction, as you can see in the diagrams. What does this mean physically? Well, the quantization of the winding number indicates that these spin structures can only be created and destroyed as a unit. So even under some external perturbation, they still retain their winding number and can be seen as fixed particles. Merons and antimerons are a special class of topological spin structures for which the winding number is equal to plus or minus a half. This means that the spin structure wraps around half a sphere, and as a result, the spins at the boundary are not uniform, as you can see in these diagrams, the black diagrams. This violates the second criterion that I mentioned before, and therefore merons and antimerons are not topologically protected, or that their winding number cannot stay unchanged under smooth deformations if they're only singly present in the material. But if you put them together, if you put two of them together, they do form a uniform boundary, and therefore they become topologically protected. Okay. The aim of my project is to detect merons in a sample of platinum co-fed iridium through a very indirect method to plot the magnetization curves for magnetization versus applied field for different temperatures of the sample.
Yes, the main aim of my project was to plot the magnetic susceptibility as a function of temperature and fit that to the modified Juli law we see here. An important note is that we also wanted to find the Juli constant for the material, which can later find the effective moment of the atoms within the material and see what they actually are, and not just based on the theoretical voltage. function we used earlier, which doesn't take into account the interactions between atoms. We also want to check whether the orientation of the sample had any effect on susceptibility.
This is a picture of the PPMS, or the physical property measurement system, and it's the instrument utilized to obtain our magnetization curves. So inside this instrument, there are two superconducting coils that apply uniform magnetic field to our sample. An oscillator then vibrates the sample, so the magnetization within the sample induces a voltage in the detector coils. And using the sample's motion, the machine then induces magnetization and plots it. For my experiment, the PPMS cools the sample down to some target temperature, then varies the field from -7 Tesla to 7 Tesla, and then back to -7 Tesla again, and plots the magnetization. So why is the field range swept across twice? This is because some magnetic materials exhibit hysteresis, meaning that the magnetization depends on the history of fields applied to it, so that the magnetization curve would look differently based on if you're sweeping through the field range the first time or the second time.
Yes. During my study, we more focused on the temperature dependence of susceptibility, which means we started with 300 Kelvin, cooling down the sample without the magnetic field down to 5 Kelvin, where we heated it up and measured the susceptibility as temperature evolved. After we reacted with the magnetic field higher than 5 Kelvin. After we heated up 300 Kelvin, we left the magnetic field on while we cooled it again. This is because for some materials, there's a difference on whether you had a magnetic field active when you were cooling the sample or not. I did the measurements again up to 300 Kelvin. We also did this again for different orientation of the sample. We also did some sweeping of magnetic field like Eugene, but this was not the main purpose of the study, as we weren't expecting to find any hysteresis, but we still wanted to make sure. And these are the three different rotations of sample, labeled the A, B, and C axis respectively.
So here are my results. These are the magnetization curves of my sample for different temperatures. And although they're colorful, they're pretty difficult to interpret because even though the hysteresis loop is present, it's not visible. Therefore, I have plotted the X and Y intercepts of both the up and down swept curves against temperature. And here the blue dots are the downswept curves and the red dots correspond to the upswept curves. So these intercepts have really fancy names. The X intercept is called the coercive field, which is over there. And then the Y intercept is called remnant magnetization. What's important to note is that both the magnitudes of these intercepts are positively correlated with the size of the hysteresis loop. So generally for this diagram, you can see that the hysteresis loop narrows as one goes to higher temperatures. And this is because thermal fluctuations make the system less stiff when responding to an external magnetic field. But if one inspects more closely, one can see that the data points for both graphs, the blue and the red dots, differ in sign until one increases temperature to 150 Kelvin. So something interesting happens there, which I like you to keep in mind. I've also extracted the saturation magnetization, or the magnetization the material plateaus at as one goes to infinitely high fields, and plotted it against temperature to the power of 3/2 to see if it fits Bloch's law. And indeed it does, quite perfectly, as you can see by the straight line going through the 4 dots. And okay, but this only applies to temperatures ranging from 150 to 300 Kelvin. So at least we have evidence that my material behaves like a ferromagnet for high fields and high temperatures. Okay, all of my results above seem to point to something interesting happened at 150 Kelvin. But to see what that is, I have plotted the derivative of magnetization with respect to applied field against applied field for all of my temperature values. And I call that the differential susceptibility. So from these diagrams, you can see that the differential susceptibility remains close to 0 until it rises in a central symmetric hill, which broadens as one goes from 5 Kelvin to 150 Kelvin, but then narrows from 150 to 300 Kelvin. On top of these hills, one can see some jagged peaks, they become increasingly pronounced as one goes to 150 Kelvin, they retain their shape beyond that temperature. This is evidence, or this is a sign that these peaks do not correspond to measurement noise, but rather correspond to distinct phase changes within our system. But what do they mean anyways? I'd say that they indicate that the field has forced a whole group of spins to align simultaneously, much like the creation of topological spin structures, and in my case, merons. After a long, tedious calculation, I have found that The Hill indifferential susceptibility most likely corresponds to two conical phases present in my system. And by conical phase, I mean that the spins in the material swirl around the central axis, which is in the same direction as my applied field. And as the field strength increases, these spins will start to align with the axis. And in the end, for infinitely high fields, they will almost align with it, but not completely. But what's important to note is that out of these two solutions, one implies a very positive fields and one implies a very negative fields. This leaves a gap in the middle, which paired with my observations from before, I suspect to be the melon phase. And therefore, I draw the conclusion that the melon phase of my sample is thermally activated at 150 Kelvin and at low fields.
Yes, and here we can see the data from my results. You can see that for the A-axis, there is a difference on whether you had a magnetic field activated during the cooling process, where ZFC stands for 0 for cool and FC stands for field cool. But that's only for the A-axis that we see the difference. You can also note that the susceptibility is higher for the B-axis compared to the A-axis for the entire temperature range. And this is an easy axis of magnetization, which is used for future applications. You can also see that the C-axis looks quite different from those two axes. It's also very noisy due to the higher surface contributions and small magnetic moment generated. Other than that, I haven't had time to, there's not been part of the study to analyze exactly what's happening here, so I don't have that many answers. When we swept the magnetic field, we can see for the B-axis is, as we expected, completely linear. If you do a linear fit, since the R-squared value is basically 1. And that's valid for a large variety of temperatures. The C-axis is once again messy, a bit of noise, and it's not completely linear. At the same time, we do not see any signs of magnetic hysteresis, so that's once again something to look into for future studies. When we used the modified Curie-Weiss law up here to fit some graphs to the data, we can extract some Curie constants. The reason the temperature range was chosen from 50 Kelvin up was that if you pick the entire temperature range, the fits become quite unphysical. And because the Curie-Weiss law is only really expected to be followed at high temperatures, it's okay to exclude the low temperature ranges. Here are some of the exact Curie constants with one standard deviation also labeled as plus minus. And using this formula right here, we can calculate the effective moment from the Curie constant. And we see that it's quite different from one we theoretically expected when just considering free ions. This means that the interactions between the atoms within the permanent terminate plays a big role in actually determining the susceptibility and the magnetic moments of the atoms. And this is something called itinerant magnetism, which we now know is present heavily in this material.
All right, as a conclusion, I will repeat what I said earlier. I found the melon phase in the sample platinum, cofab, iridium is thermally activated at 150 Kelvin and at low fields.
Yes, and my conclusion is that there is some anisotropic effects, which means that the orientation of the sample does matter in the susceptibility, and there is a difference between the theoretically predicted magnetic moments of the ions and the actual measured effective magnetic moments for the atoms within permanent terminate. Yeah. Questions?
Yeah. So about merons, I mean, what's so interesting about them compared to other phases, like other spin topological orientations?
Well, the names and properties of merons. Their spins mostly lie in the plane of the material, and so they're less stiff compared to other types of topological spin structures that have spins protruding from the material. And other than that, they're easier to manipulate because they're half a regular skyrmion where the topological number, where the winding number is 1.
Yeah, interesting. And about the ultramagnets, the itinerant magnetism you were talking about, is that specifically because of the ultramagnetism, or is it a material property of this thing you're looking at?
No, there's magnetic materials which exhibit itinerant magnetism. So basically it means that the interaction between atoms in material plays a major role, and it's not just, you can't just look at the individual atom and predict how the susceptibility is going to look. We have found that this specific ultramagnet does exhibit that, but it's not something unique to just ultramagnet.
Right, yeah.
Yes?
And the fact that merons are thermally activated at 150 Kelvin, what does that entail for the usage of meron in proposed usages? Like, and also, what would those be? Like, are we talking quantum computing or?
Oh, yeah, you can definitely use those to encode information really densely, and you can manipulate the data very quickly using very small energy. And yeah, so they're found at 150 Kelvin in the sample. That's where you locate them.
Like, they stop existing at lower temperatures.
Yeah, that's at least what we found, where they're not as abundant. Because we only have the magnetization curves. We can't spot them directly.
Like, that's surprisingly high temperatures for quantum states in general.
Yeah, well, in the paper I read, they found the neurons at room temperature.
Damn, all right.
Yeah. Any more questions? Or? What?
Thank you, Gabriel and Georgie. That was the last presentation for lunch. So now we have lunch until 12:45 when we start again. Thank you all for this presentation this morning. It's been so much fun. Welcome back, everyone. Now I'll start the introduction of this next presentation by Eleverna, Summer, and Paulina. So Eleverna studies at the Katedralskolan in Växjö. She has a strong passion for neurology and astronomy, and she has held the position of Student Council President and works part-time in retail. Her interest in science was sparked early, and she regularly participates in her school's science activities and astronomy evenings. Paulina is enrolled in the Natural Science program at Presentera in Helsingborg. She is deeply interested in biology, especially oncology and immunology, which she explores further through research schools and student organizations. Paulina has founded a science committee at her school and writes for the youth science magazine Particular. And Summer attends the Natural Science program at Kungsholmens gymnasium, Stockholms musikgymnasium. She is passionate about neuroscience, biotechnology, and artificial intelligence, and has taken part in advanced camps in mathematics and programming. Outside of her studies, Summer is an active dancer and instructor, and enjoys oil painting and music. During the research project at Karolinska Institutet, Eleverna, Paulina, and Summer worked under the guidance of Dr. Chloe Moello. Welcome up. Hi? No, okay. Yes.
Ja, okej. Neurodegenerative diseases are disorders that gradually degrade neurons in the nervous system, particularly in the brain. To treat neurological diseases such as Alzheimer's disease, therapeutics need to access nerve cells. However, there are many limitations that restrict the neural accessibility, one of which is the blood-brain barrier. That prevents roughly 98% of all studied drugs from entering the brain. The blood-brain barrier, also known as the BBB, is a filtering layer of different cell types that surround blood vessels in the brain. The BBB is a protective barrier, acts as a protective filter that inhibits most molecules from passing the barrier acts as a protective filter, inhibiting most molecules from passing to the nerve cells. So, in order to prevent neural damage and to maintain brain homeostasis. The first layer of the BBB is a monolayer of endothelial cells that cover the inner walls of blood vessels in the brain. These cells are closely joined by tight junctions that inhibit most molecules from passing between these cells, unlike other endothelial cells outside the body. The endothelial cells in the brain are embedded in the basement membrane, and parasites and astrocyte envy, working together to regulate blood flow and exchanges between the blood circulation and other brain cells such as the microglia, oligodendrocytes, and neurons. Altogether, these cells form the neurovascular unit, as shown in the picture here.
Thank you.
So yeah, the glucose domain acts as a molecular chaperone, which means that it helps proteins to fold properly and to avoid aggregating. Now, this function is essential in diseases such as Alzheimer's disease, since when proteins misfold, like amyloid beta, they form plaques, which damages brain cells. And studies have shown that glucose domain can reduce aggregation, which makes it a strong therapeutic candidate for neurodegenerative disease research. But what makes glucose especially valuable is the fact that it can cross the blood-brain barrier. So in vitro, as shown in this blue histogram here, as well as in mice after invasive injection. And moreover, when fused with a cargo protein like the NT, like a spider silk domain NT, the glucose domain can transport with cargo across the blood-brain barrier, both in vitro, shown in this white histogram, and also in vivo in mice. So the immunofluorescence image shows that like the pink dots on there are the anti-glucose, and it's been detected in nerves and other brain cells, shown with the cyan blue dots over there. So yeah, our research question states which intracellular vesicle pathway mediates the transcytosis of glucose across human brain endothelial cells.
And yes, to answer this question, we have used an in vitro model of the WB, as seen in this insert here, which consists of one monolayer of the endothelial cells. So in this minimalist model of the WB, we have the apical part, which represents the blood, and we have the basolateral side, which represents the brain. And these two sides are separated by the layer of endothelial cells. So when a protein is added into the apical side, it simulates the transport from the blood through the monolayer and down to the brain. And we use a time-lapse analysis to examine the gradual transport over time. So we start off with the cell culture that has been grown for 6 days, and the different incubation times of 2, 15, 30, and 60 minutes were tested with the NT-glucose. And the incubation was done with NT, which is a solubility tag derived from spider silk protein, which is used to fuse with the glucose protein. And NT is not expressed in endothelial cells, which facilitates the tracking of the transport without any endogenous interference. So after the incubation, the cell culture media was removed, and we washed the cells to detach non-specifically attached proteins from the surface for clear staining. And this was also done on ice to stop the uptake of NT-glucose. Then the cells were fixed with PFA. The cells were also permeabilized with 2020, which can create small holes in the cell membrane to let the antibodies easily go inside the cells and bind to the target proteins. And then the cells were blocked, as in this step here. So cells were blocked to let the primary antibodies bind specifically. The cells afterwards were incubated overnight with the primary antibodies of rabbit anti-NT antibody that is used to detect the anti-glucose, and either the anti-EEA1 antibody with the host of mouse, and also, or either the mouse anti-LAMP1 antibody, which are used to detect early endosomes or lysosomes respectively. And lastly, for the process, we have the incubation of cells with the secondary antibodies, which are conjugated to fluorochromes to detect the primary antibodies. And this was also done with phalodine, which stains the F-actin filaments, and the DAPI, which stains the cell nuclei. For the cutting membrane and mounting, so we use scalpel and tweezers to cut the membrane from the bottom of the insert. We took the membrane, put the cells on top of the microscopy slide. We put a drop of mounting media, and the cover slip was used to seal the cells. And the samples could be examined in the confocal microscope.
A 3D modelization of these endothelial cells was made for 2, 15, 30, and 60 minutes of incubation with NT-glucose. So what we see here is the cell layers, the apical, the top part, and bottom part, which is the lateral part. So at 2 minutes, we see that anti-glucose is only present in the apical part. This means that the protein has been absorbed by the cell, but that the cell has not had enough time to start the transport of it. By 50 minutes, we see that the cell has had enough time. Well, anti-glucose is represented by the pink color, and early endosomes, which are the vesicles that transport the protein across the cell, is represented with the cyanide staining, and cell nuclei is represented with blue staining. And by 15 minutes, we can see that the cell has had enough time to transport the protein to the section part, but not enough to transport it to the bottom layer. Within 30 and 60 minutes, we see that anti-glucose is present across the entire cell. So the protein domain is present in the apical, midsection, and basolateral layer, suggesting that transcytosis of the protein domain was successful. In these pictures, we can see the immunofluorescent staining of the endothelial cells incubated with anti-glucose for 2 minutes. And these pictures show the pictures of the apical layer, and the pictures below show the basal layer. So, as you can see, anti-glucose staining was mostly localized, diffused and distributed across the cell membrane. In this little image of the anti-staining for the apical part. And there was also a minimal amount of vesicular staining observed for the apical layer. We can also see that there is no detectable anti-glucose in the basal layer, which suggests that the cell has not had enough time to transport it. The co-localization or co-staining between anti-glucose and early endosomes are marked with red circles, as you can see in this picture. And within 2 minutes, there were minimal amount of co-stainings detected, as you can see in the picture. After 15 minutes, the amount of vesicular staining has increased quite a lot, and however, the basolateral layer was still unstable, remained unstable to glucose, because the cell has still not had enough time to transport the protein across the bottom layer. We can also see that the number of localizations between anti-glucose and early endosomes has increased. However, there are still many early endosome vesicle stainings that do not co-state with anti-glucose, which means that there were early endosomes detected, but without anti-glucose presence in them.
Okay, yeah, so at 30 minutes, we can see still visible localization at the apical membrane, indicating that the endothelial cells still taking anti-glucose in a continuous way. We can also see clear co-localization here. And as for the basolateral membrane, we can see a clear localization and co-localization, indicating that the protein has been transported through the cell in 30 minutes. For the 60 minutes time frame, we can see that vesicles positive for EA1 and anti-glucose has increased significantly, indicating that there's ongoing internalization as well as accumulation at the early endosome compartments. We can also see that there is very, very strong co-localization here. And for the basolateral membrane, there's a sustained localization and co-localization, indicating that the anti-glucose is present with early endosomes at this time frame. So this means that there's successful transcytosis. So we also did staining for the lysosomes, shown here, marked with LAP1, and for 60 minutes, and we can see that there's minimal co-localization here with LAP1 positive lysosomes. So when endothelial cells internalize molecules, they use a process called endocytosis, in which the membrane engulfs external material and is transported through a network of vesicles. So once internalized, it can be recycled It can be degraded, which we don't want. It can go to degolgi through retrograde, or it can be transcytosed with early endosomes through the cell. And our results show that anti-glucosidase follows a transcytotic pathway with early endosomes, and it avoids lysosomal degradation, meaning that it enables efficient transport across the endothelial cells.
Yes, so with this study, we also have a few limitations that should be considered. So the method focuses on the endothelial monolayer. Not all the cell layers in BBB is at present in vitro, which we have studied. So this can make it difficult to evaluate if the glucose can really pass through the BBB in vivo conditions. So to provide a more representative model for this, we could use an in vitro study examining co-culture of both endothelial cells and astrocytes. And additionally, only qualitative data were considered in this internship. So this analysis allowed us to identify the vesicles transporting B2 glucose across the endothelial monolayer. However, a quantitative data could complete this analysis with the quantification of early endosome vesicles over time to see if glucose can trigger any endocytosis mechanisms within the cell. And for further research conducted on additional experiments investigating the intracellular vesicular pathways involved in transports, for example, the retrimers or the recycling endosomes, could be beneficial to gain a greater insight on the transcytosis process. And as mentioned before, this study that we've done has focused on in vitro experiments that only focuses on one layer of the BB, while the BB has many cell layers. So to evaluate the results that we've gotten in vitro, we could use an in vivo experiment, as in within the living organism, to evaluate the relevance of the in vitro data that we have obtained.
Yes, and this study deepens the understanding of the B2 glucose permeability across the blood-brain barrier in this in vitro model consisting of a monolayer of hematocerebral microvascular endothelial cells. The results reveal that the protein domain is actively absorbed within 2 minutes of incubation, that it is successfully transcytosed within 30 minutes of incubation, and that its main pathway is predominantly directed towards the early endosomal compartments instead of lysosomes for degradation, which suggests that the B2 glucose domain could potentially be a suitable candidate for delivering medicine through the blood-brain barrier to treat neurological diseases. Yes.
Yeah, so we would like to extend our greatest gratitude to our mentor, Dr. Kluing-Wello, for your dedicated mentorship and guidance for this project. It has been a privilege to be under your supervision. We would like to thank Jan Johansson for being able to be a part of this project, as well as all organizers of Roots for Excellence for your guidance throughout this program. And we would also like to thank our partners, AstraZeneca, Ole Stiftelsen, and Böje Stiftelsen, for making this possible. Thank you.
So if I understood things correctly, you had some figures with some colorings, magenta and green and blue. Yeah, were these like colorings made afterwards, or like what? How do you
like the immunofluorescence staining?
Yeah.
Yeah, so we did it like during the method.
Yes, so the antibodies have fluorophores.
Yeah, this one, that's the coloring.
Yes.
Yeah, so we incubated with chimeras and antibody. So it can be attached.
What was it like? Some kind of how did the colors differ between the different? Like they were different colors, right?
Yeah, so we did like separate for like the early endosomes and for the lysosomes. So it's the same coloring essentially, but almost, but like we did like separate like tests, so we could like separate. Yeah.
Okay, that makes sense.
Imagine that. Yeah, you have this question.
Yeah. So the colocalization of endosomes and anti-brighthouse was like it was not one-to-one. Does this mean that things went through important glucose? I mean, what was other things coming through? Like,
what do you mean? Like,
it looks like there's more because it looks like there's more endosomes than you guys have.
Yeah, that suggests that the anti-glucose has multiple pathways and not only a single pathway, but we transfer it to other.
So recycling endosomes could also be a pathway.
Yeah.
All right.
Like what other difficulties could the other layers which you did not account for bring to this method?
Excuse me, can you just repeat the question again?
In your experiment, you only observed the specific layer present in the body and discounted for all the others. How would they actually affect the result?
So the BB has a lot of layers, so we're kind of also, it's another further study that we can do. We've only focused on the endothelial cells for this time. So we just suggested that we could do an individual study of the co-culture of both astrocytes and endothelial cells that are both in the BB.
Yeah, but do you have any suspicions of how they might affect the results?
Further studies are.
Again.
Yes, because we don't know a lot about the transcytosis process either, because they're different receptor mediated ones.
Gotcha.
Further studies. Any more questions? Yeah, thank you.
Thank you very much for that presentation. Next up, we'd like to welcome Tingshan Shao to the stage. Tina is a student in the technology program at the Täby Enskilda Gymnasium. With a strong background in programming, mathematics, and cybersecurity, she has participated in several coding camps and competitions with excellent results. Her academic interests include dimension theory, game theory, and quantum physics. And she also brings years of dedication to dance, where she is both a performer and an enthusiast. During her research project at KTH, Tina worked under the guidance of her mentor, Cyril Arto. So let's give a warm applause to Tina.
Hello, welcome to this presentation on automating complex refactoring software tests using ChatGPT. So when designing softwares like, for example, video games, you'll often add new features or fixes to improve the game. But how do you make sure that these changes don't cause bugs or introduce new errors? Well, what software engineers do is they run tests on the program to make sure that everything functions as intended. And the testing software in this project was the model-based testing tool Jobbat. So in short, model-based testing uses an abstract model to generate test cases from specifications and requirements. And these test cases are then run on the software to make sure it matches with the model. As you would expect, the faster the test cases run, the more time you will save overall. And this is essential to not waste too much time on just testing the software rather than actually developing the software. So that is why we optimized the testing speed of the Jobbat in this project. And yes, and here is how the code was worked. So we optimized the testing speed of my bad, using or refactoring the code, which is changing the structure without actually changing the external behaviors. So here is the code refactoring. So first, in the old framework, these boxes represent the Java virtual machine, which is the program that was used to execute the tests. And then the green circles are the test cases. So in the old framework, each test case was run individually, having to start the Java virtual machine or JVM over each time. But in the new framework, instead we group the test cases together to test suits. And then we only had to run the JVM once for each test suit, which optimized the time. However, converting these tests from the old to the new framework takes a lot of time to do manually. It is therefore tempting to use a generative AI like ChatGPT to automate this process for us. So in this project, we used the ChatGPT model GPT-4o Mini to try to automate this process using different prompts and varied prompts, and we also analyzed how different prompts could get different outputs. So we started to manually convert the test to get a more understanding of the actual process. And we then formulated prompts and sent to ChatGPT to automate this process. And the prompt, we used 3 prompt variants in this project. So the first one tried to solve the full problem, while the other 2 tried to solve different smaller parts of the whole process, where the second prompt variant focused on a larger part than the third. And then we started the prompting. So we sent an initial prompt to ChatGPT, and then it generated a script, which we copied into the terminal and executed it. And then if an error appeared, we would copy the error message back to the ChatGPT within the same conversation. And we will make it to refine this code and generate a new one. And otherwise, if no error appeared, but the outcome was still not the desired one, we manually refined the prompt and started a new conversation. Or otherwise, if the conversion was successful compared to our manual conversion, we recorded the prompt that led to this successful result. And for the bigger prompt variants, so the prompt variant 1 and 2, we also found a prompt that differed a lot in language and structure, and to analyze and compare how different prompts gave different outputs. So here is a quick overview of all the 5 prompts that was analyzed in this project. And then we summarized all the results in a few different diagrams. Here are the outcomes of each step in all the prompts. So where a step meant a new prompt within the same conversation. And we encountered a few different errors. For example, the syntax error meant that the code was wrongly written, maybe having an extra parenthesis or quotation mark. And we also analyzed the code sizes, and it's interesting to see how the first prompt 1.1 is a lot longer than the third, or the last prompt, prompt 3. We also encountered some different problems with ChatGPT. For example, it sometimes did not follow all our specifications and selectively ignored some of them. And also, the same prompt could generate different answers in different conversations, which suggests a level of randomness for ChatGPT. And sometimes it also forgot our earlier prompts that we sent within the same conversation. So when analyzing the length of the output in the lines of code, we can see that the prompt 1.1, which has more verbose, and casual language also generated a longer script with more detailed comments. Compared to prompt 1.2, which actually tried to solve the exact problem, but the length was a lot shorter. This is also because 1.2 had more concise language in the prompt. Another reason why they differed so much in the length was that ChatGPT in prompt 1.1 actually misunderstood some of the instructions. So we wanted ChatGPT to only convert one single test, but in prompt 1.1 it actually tried to convert all the test cases. We also analyzed the success rate, and we can see that prompt 1.2, 2.2, and 3 all reached success with fewer steps, and also 2 of them reached full success. And these 3 prompts used more information dense and concise language. And then we also observed that there were some limitations of ChatGPT. So when we tried to prompt ChatGPT with very long and a lot of information in the prompts, it generated not so good results, as 1.1 and 1.2 tried to solve the full problem, but they both never reached full success. Instead, when we broke up the problem into smaller tasks, so in the other 3 prompts, they reached more success. And we also, as mentioned before, ChatGPT gave inconsistent answers, even for the same prompt. So future research can focus on more recent and advanced generative AI models and also a larger variety of different AIs to compare similarities and differences, and also see more general characteristics. So in conclusion, this project investigated how the ChatGPT model GPT-4o Mini could automate a complex test conversion process using different prompts and strategies. Although it could not automate the full process using a single prompt, it was able to automate some parts when breaking the problem up into smaller tasks. And using ChatGPT could be beneficial if it reduced the time and the manual effort. So if ChatGPT continues to improve in the future, it can become even more beneficial to use. And I would like to thank my mentor, Cyril Artho, for these 2 weeks at KTH and for guiding me through this project, giving me a lot of support, help, and feedback. I also want to thank all the experts who have been reading my report and giving me very valuable feedback. And as well as I'm very deeply indebted to Race for Excellence and their partners Tage Svans stiftelse för undervisning och forskning and Jakob Wallenberg stiftelse Särskilda fonden for giving me this opportunity and making this project possible, especially the organizers of Race. Thanks for these 4 weeks where I have learned a lot, and it has been really, really rewarding. So thanks to all of you who have contributed to this project, and thanks to all of you who have listened to this presentation.
You may have mentioned this, but you give it a chance to fix its own code if it messed up. Could you prompt it again and say could you debug this, or were you just stopping when it gave up, or when it gave bad code?
Can you repeat?
I mean, when you say it failed to produce a useful test, does it mean that it's failed totally, or did it? I mean, did you give it a chance to maybe debug itself? Like,
if there was an error message, I would copy it back and send it.
Yes.
But otherwise, if the outcome was wrong, I would try to formulate a new prompt that try to fix this error.
Okay, so all the error messages were fed back, but it was just wrong output, then you just cut it off basically. So
Yes.
Okay.
Yes.
Do you think the results would have been like different if you had used another ChatGPT model, like O1, for example?
I think, well, further research can be done on that. To investigate how different models different to each other. Yes. Yes.
Like, how many times did you actually prompt ChatGPT with each prompt before giving up? Because you said they were like randomness driven. Like, to what extent was that present, and how much toleration did you?
Well, I prompted around 10 to 20 times, or conversations.
And like, were there things like, if it ever failed once, would it like almost never succeed again, or how?
Do you mean?
If a prompt was successful in creating code that worked for the purpose, would that same prompt almost always create useful code, or how bad would the randomness be?
I think that sometimes the prompt that generated the successful result actually also sometimes could generate an unsuccessful result. So it varied a bit.
Okay, but you didn't find, like, were there noticeable prompts that were a lot better than others, and were there any themes like in the wording used, except for like formal or non-formal, very giving code explicitly?
Well, just adding more details to the code.
Details in general
was better. Yes. Yes.
You said you did manual conversion at the start, so I have two questions about that. How many lines of code did that manual conversion generate? If you compare it to what ChatGPT managed to do.
The manual conversion, it was so. I didn't explain it in this presentation because it's a bit long, but I had to convert the code, which was the original code was like 1-2 lines, and then the converted code was a bit longer, not so much, it was like 5-6 lines. But then I also had to change the format. I had to change the files and a lot more. So it was a more complex process.
So you would say that it was shorter than the shortest ChatGPT generated code, or longer?
What do you mean?
No, I mean, when you did the manual conversion, I'm thinking you also generated some new code, and that had some. It was the number of.
My manual conversion wasn't generating the script for doing this process. My manual conversion was just like doing the process.
So it's difficult to compare with what ChatGPT did. It was just to get you. It's difficult to compare the process of the manual conversion to what ChatGPT did. That's what you're saying.
Yeah.
Okay.
I think so.
How long time did it take to do the manual conversion?
Well, we didn't convert all the code. We just converted some of it. So it's hard to compare them. How long time?
Okay.
Yes. Yeah. Thank you.
Thank you, Tina. And now it's time for Isabel Linder and Erik Sund to present. Isabelle is entering her final year of the Natural Sciences program at Victor Rydbergs Gymnasium, Djursholm. With a background as an elite athlete in team gymnastics, Isabelle has also taken on roles as both a judge and coach. A year as an exchange student at Palo Alto High School in California sparked her interest in science. And today, she's especially drawn to cancer research and genetic engineering, with a focus on hereditary diseases. Erik studies the Natural Sciences program at Civitas Privata Gymnasium in Malmö. He has a strong fascination with the brain, Alzheimer's disease, and nanotechnology. Erik has participated in several science Olympiads and took part in a course So You Want to Be a Surgeon at the University of Hong Kong. In his spare time, he plays piano and tennis. During the research project at Karolinska Institutet, Isabelle and Erik worked under the supervision of Professor Ute Römling. Welcome up, Isabelle and Erik.
Thank you, Hannah. People. Millions of people all around the world suffers from chronic infections, such as cystic fibrosis. A major reason behind the persistence, biofilm, dense, complex communities of bacteria, microorganisms that are persistent to the most potent antibiotics. But what are biofilms? Biofilms are groups of microorganisms that attach themselves to surfaces and enclose themselves in an extracellular matrix. The extracellular matrix is made up by polysaccharides, proteins, DNA, and lipids. It offers support, stability, and an environment for nutrient exchange and signaling. The biofilm formation starts with the initial attachment, where pathogenic cells, using the flagella, find a suitable surface to attach themselves to build an extracellular matrix. When the extracellular matrix has become mature, some of the pathogenic cells are re-released into the world to recolonize different places. Different microorganisms and bacteria prefers different environments. Temperatures around 30 to 37 degrees are preferable for majority of bacteria for optimal growth, due to them stimulating their metabolisms and increasing the production of the extracellular matrix. Salt levels around 0.5% to 2.5% are optimal for many bacterial growths, due to them stimulating some of the genes for the extracellular matrix and the cell and surface adhesion. Salt levels above that, 3% or more, can cause osmotic damage, dehydrating the cells, and causing the cell death. This is relevant due to antibiotic resistance. Antibiotics have a very hard time penetrating the extracellular matrix due to its dense and complex structure. And even if the antibiotics are able to penetrate the extracellular matrix, they're met by a very low oxygen environment, where some of the cells, bacterial microorganisms, turn into a persistent state, where they are protected from all the antibiotics. When the antibiotics are dealt with, they return to a pre-persistent state, where they continue with the infections. A way to detect biofilms is by using Congo red dye. Congo red dye works as they stain the cellulose in the extracellular matrix. Another way to identify and detect biofilm is by looking at texture. Due to the bacteria going upwards when creating the extracellular matrix, they create a rough texture, signifying extracellular matrix growth. When the bacteria is both red and have a rough texture, it indicates that there is a strong production of an extracellular matrix, in other words, a strong biofilm. If the bacteria is only red, it indicates that it contains cellulose, but not necessarily extracellular matrix. If the bacteria is only rough, It indicates an external matrix, but not containing cellulose. The aim of our study is to see how bacteria from algae grow in different temperatures and in different salt conditions, and see if these bacteria can grow biofilm or not.
To characterize the bacterial strains, we performed two different tests. One to measure bacterial growth in different conditions, and the second was a biofilm formation assay. To perform these tests, we first prepared two different media, a liquid LB and a congruent media, both with and without sodium chloride. The bacterial growth was measured using OD or spectrophotometry. So liquid LB media was inoculated with the 11 bacterial strains and placed into microplates. These were then incubated at 4 different temperatures, 18, 24, 30, and 37 degrees Celsius. After 40 hours, the optical density of each test was measured to check if any bacterial growth had occurred. The biofilm formation assay was performed by placing a small amount of each bacterial strain onto a congruent plate. These were then incubated at 28 degrees Celsius, and after 72 hours, plates were photographed, and any changes in texture or color was noted. Based on our results, 8 of the strains preferred 30 degrees Celsius, and only 1 preferred 37 degrees Celsius, strain 17M63. These results are expected as Eric was mentioned before, higher temperatures usually encourage bacterial growth. It also is consistent with the origin of the bacteria, since they originate from algae and are therefore adapted to relatively warm environments. This graph shows the difference between bacterial growth in media containing sodium chloride and media not containing sodium chloride. So to ensure accuracy, strains with inconsistent readings were removed, but they are available in our full report. A positive value indicates that the bacteria grew better in media containing salt. So as you can see, this is the case for strain 7, KML2, 11 Fed1, and 20 LB small. The only strain that preferred media not containing sodium chloride was 19 AmpSC. And interestingly, strain 25 KN1 preferred media not containing sodium chloride for lower temperatures, but media containing sodium chloride for higher temperatures. Once again, these results are consistent with previous findings. Sodium chloride is a standard component of LB media that regulates osmotic pressure and which promotes bacterial growth. It also indicates that the bacterial strains are adapted to saline conditions, which is once again consistent with their origin from algae. 19 AmpSC's results indicate that it's probably adapted to less saline conditions. The results for strain 25 could be explained by temperature-induced stress responses that affects how bacteria reacts or handles salt concentration.
The results of the biofilm assay shows us that 3 of the 11 strains became rough, while 5 of the strains turned red. The most promising result, however, is the 25 KN1 that show both red color and rough texture, indicating good biofilm formation. When comparing 25 KN1 without sodium chloride and 25 KN1 with sodium chloride, we can clearly see that the 25 KN1 without sodium chloride show a much more intense color and rough texture. This might seem contradictory, considering the fact that salt is supposed to enhance the growth of the biofilms. However, as I previously stated, too high concentration of salt can lead to osmotic damage, leading to the death of cells.
It is also important to mention that we have several sources of error in this project. Most importantly, there's always a risk of contamination when working with bacteria. Our original method used to determine bacterial growth had to be replaced due to severe contamination of several strains. The method included manually sampling the strings multiple times, which created many opportunities for contamination. By switching to microplates, the need for manual sampling was removed, and therefore the risk for contamination minimized, although it can never be fully eliminated. This is also an issue when working with our congruent plates, especially during inoculation, when mixing up bacterial strains or introducing foreign bacteria could affect our results, which is shown on this plate above, where one of our congruent plates was contaminated during inoculation. Another source of error are instrumental limitations or inaccurate readings. Bacterial growth was once again measured using spectrophotometry, and these sorts of measurements always have a margin of error. Since bacterial growth was very small in some conditions, and therefore also the difference in optical density, this margin of error may have affected our interpretation of the results, therefore affecting the accuracy of the study.
So, in conclusion, when in bacterial growth, temperatures for 30 Celsius with salt show the best environment for majority of all bacteria. But however, in biofilm formation, the environment without salt showed us better biofilm formation. Further research should be done to be able to find more and different strains of bacteria and see how different factors such as pH can affect the biofilm formation. We would like to thank our mentor and supervisor, Ute Rövning and Roman Sidorov, for all the support we gave and all the help. We also like to thank Race for excellence, for giving us the fantastic opportunity to be here and conduct our research. We also like to thank Karolinska Institutet for giving us a place for our research. And lastly, we'd like to thank AstraZeneca, Stiftelsen Oskar och Marie Ekmans donationsfond. Thank you, everybody.
I'm really curious, why algae?
We received those samples, so yeah, I don't know why we should receive this out. Yeah.
Fair enough. And for the salt,
yeah,
it was like an on-off thing. The samples with the salt, what was the concentration?
Ooh, I'm unsure. We use
Concentration of salt?
Yeah.
We had 2 grams for 400 milliliters of water.
Is that comparable to seawater?
I'm not sure.
Okay.
More questions? Thank you.
All right, we're once again a bit ahead of schedule, so we'll take another small break until 13:54, and then we'll be back here. All right, welcome back. Next up, we have Albert Mörling-Wipf, Gustav Dagin, and Nico Kai. Albert studies the Natural Sciences program at Norra Real in Stockholm, with advanced mathematics courses at KTH. He has a strong interest in physics, especially plasma physics and computer simulations, and is an active member of several science clubs. Albert also has a background in international choir singing and plays multiple instruments. Gustav is in his second year of the Natural Sciences program at Täby Enskilda Gymnasium. His passion for mathematics and science was rekindled through a math competition, which sparked his deep involvement in various scientific contests, where he has achieved strong results. Gustav has also founded a math competition for middle school students and competes at the junior elite level in orienteering. Nico studies the Natural Sciences program at Victor Rydberg campus. His passion for math and physics shines through participation in competitions such as school math contests and the Wallenberg Physics Prize. Nico applies his physics knowledge to analyze conditions in sailing and paddling, sports in which he actively competes. During the research project at KTH, Albert, Gustav, and Nico worked under the supervision of Dr. Ashna Ray. So let's give a warm applause for this presentation.
I will start off with a question for the audience. How much of the energy generated worldwide do you guys think is lost as thermal energy, also known as waste heat? And it could be through huge smokestacks like these, or through heat losses in industrial processes. Take some time to think about that. Now, I want those who think that around 5% is wasted to raise their hands. All right. All of you think it's more than that? All right. How about 10%? All right. Still all right. How about 20%? Now think about that. That's 1/5 of all the energy generated. Right? Because you guys still think it's more? How about 50%? All right. Now we got a few more hands up. Well, the actual value is 72%. 72% of the energy generated is lost through thermal energy. Just imagine what we could do if we could reuse all of that thermal energy.
Yeah, and that is exactly what we've been working with for the last 2 weeks. My name is Gustav.
I'm Nico.
And I'm Albert.
As we have already explored, a significant portion of all energy generated is lost as heat, unused and into the environment. However, thermal energy storage systems offer a promising and efficient way to store and utilize this energy. Now, thermal energy systems are generally categorized into 3 groups: sensible heat storage, thermochemical storage, and latent heat storage. Now, sensible heat storage is the most basic and simple form of thermal energy storage. It relies on the temperature change within a solid or liquid medium. The energy stored in a sensible heat storage system is directly proportional to the system's mass, its temperature change, and specific heat capacity. Its main advantage is its cheap price and relative simplicity. However, it lacks in terms of energy density. Now, thermochemical energy storage systems rely on a reversible chemical reaction to store and release energy. They are relatively complex, however, they have a very, very high energy potential storage density. Now, sensible heat storage systems rely on the phase change of material to store and release energy. And the key materials enabling this are called phase change materials, or PCMs.
Thank you. And so here we see a graph showing the temperature as a function of thermal energy for a liquid to gas PCM. And there we go. The LHS part is the one we want to maximize. And we do that by maximizing the heat of vaporization in this case to as high as physically possible. The PCM that we used in our study is called an icosane and is a liquid to solid PCM. Okay, liquid to solid PCM with a solidus temperature of 308 Kelvin, so that's the temperature at which all of it is solid, and a liquidus temperature of 311 Kelvin, so that's the temperature at which all of it is solid.
In order to store energy in the PCMs, we make use of something called heat exchangers. Heat exchangers serve the purpose of transferring heat from one fluid to another fluid. And as displayed here, we have three types of common heat exchangers. Parallel flow, where the hot fluid and the cold fluid flows parallel to each other. Counterflow, where they flow opposite to each other, and cross flow, where they flow across each other, where the heat exchange mainly happens in this cross area. There are three types of heat transfer within the heat exchangers: conduction, radiation, and convection. Conduction is through heat transfer when touching another material through atomic vibrations. Radiation is heat transferred through electromagnetic waves, for example, the rays from the sun. And last but not least, convection is heat spreading through physical movements within a fluid. For example, water molecules moving from here to there.
Okay, so the main aim of this study has been to investigate the heat transfer characteristics in a PCM-based heat exchanger employing the straight-chain alkane and iocane as the storage medium. We specifically aim to do this by investigating a range of factors, including heat transfer fluid, heat exchanger configuration, inlet velocity, and temperature.
Right. All of this was done by simulation, and specifically with the help of computational fluid dynamics, which is, or CFD, which is a subfield of fluid dynamics, which specializes in simulation of fluids. There we go. And the software used was ANSYS Fluent, a commercial CFD software. And in broad terms, we can say that it's based on three governing equations: the momentum equations, the continuity equation, and the energy equation. And examples of what you can do with this is simulate the fluid flow around rocket nozzles, F1 cars, and ventilation. And it can look like this.
Okay, so let's begin with something basic I believe most of you would be familiar with since high school, for example. Newton's second law. Now, Newton's second law states that the forces acting on an object is equal to the object's mass times its acceleration. Now, or in essence, the forces acting on an object is also equal to the rate of change of momentum. Now, this principle doesn't only apply to solid objects, it also applies to liquids. However, liquids are constantly moving and deforming, so we need a more specific way to model this for fluids. And that gives us this equation. Now, I know this might look a bit complex and overwhelming, but the basic principle behind this is exactly the same as Newton's second law. So the left-hand side of this equation describes the rate of change of momentum in the fluid. And on the right-hand side, we have the forces acting on the fluid. And that includes viscous forces, pressure forces, gravity, and other external forces as well.
In order to ensure that the simulation is realistic, we need to ensure that no mass is created or destroyed within the simulation. And commonly, this equation, complicated equation, is used to describe that. However, in this project, we assume the fluids to be incompressible, meaning that they are constant in density. This means that we can simplify this complicated equation into this one.
Wonderful. And the last of the three equations is the energy equation, which is based on the first law of thermodynamics, which states that energy is always conserved. We can restate this as that the change of energy inside the system is equal to the energy added to the system minus the energy removed from it. And that gives birth to this. We won't go into details, and if you have questions, we can take them at the end of the presentation. Now, measured boundary conditions are something quite central in CFD, because as you might have recognized, all of the equations that we mentioned are partial differential equations, which are continuous in space and time. But we can't divide our domain into infinitely many and infinitely small rectangles, sadly. So instead, we will discretize it, as it's called, and divide it into small parcels in which we average the conditions. well, then you can call the domain that control volume. And it can look like this. Quite nice. Now the geometry and meshing that we used looked like this, with the hot fluid above, the cold fluid below, and the PCM in between. And the mesh looked like this, with a refinement on the PCM.
Now, to ensure that our simulation results are reliable and not influenced by the grid size we chose, we performed a grid size independent study. Now, this is a key concept within all numerical simulations, but especially within computational fluid dynamics, where the physical domain is discretized into many smaller elements. If the grid size is 2 cores, and by cores I mean that the elements are, do you hear me? Yeah, are too large, it could result in inaccuracies and issues with convergence in the simulations. However, if the grid size is too fine, and by fine I mean that the element size is too small, it may result in extensive periods of simulation and high computational costs. So we performed 5 simulations with different grid sizes to investigate the effect of grid size. We performed simulations with grid sizes ranging from 0.2 millimeters all the way down to 0.1 millimeters, with steps of 0.0 to 5 millimeters. And as you can see in these 2 graphs, as the grid size was refined, the solutions began to converge, meaning that the difference between them became increasingly smaller. At 0.125 millimeters, further refinement produced negligible results, indicating that the solution had become grid independent. We therefore chose 0.125 millimeters as the grid size, because it provided us with accurate results without unnecessary computational costs.
Now, as earlier mentioned, we assumed the fluid to be incompressible, which means that the density was constant, and therefore a pressure-based solver was used. We also adopted for a transient simulation, which meant that we could see the whole heat transfer process instead of looking for a steady-state solution. We also assumed the fluid flow to be laminar instead of turbulent, so the laminar viscous model was used. We also enabled the energy equation and the melting and solidification model of ANSYS fluids to simulate the melting of the PCM. As Gustav mentioned, the 3 variables that were chosen to be examined in this project is the heat exchanger type, the heat transfer fluid, and the fluid velocity. And as you can see here, we conducted a total of 6 simulations to investigate the impacts of each variable. Some variables, however, were kept constant. For example, the temperature of the heat transfer fluid, where the hot fluid was at 350 Kelvin and the cold fluid at 300 Kelvin.
Right, and here we have our results. And so here are the simulations of what? Yes, these 2 are the simulations with air at 5 meters per second. These 2 are with air at 10 meters per second. And here is water. This is temperature graphs, by the way. And as you can see, water seems to be reaching a steady state at 30 seconds. But the simulations with air don't reach a steady state within the simulation time. The liquid fraction. Yeah, and by the way, liquid fraction is the measure of fraction, the fraction of the PCM that is liquid. So 1 is that all of the PCM is liquid, and 0 means that it's solid. And once again, we see that, yes, these reach a steady state quite early on, but these go further. And yeah, these are the simulations with 5 meters per second air, and these are with 10 meters per second air. I believe you have more to say about this.
Yes. Now, if we compare the simulations where water was used as the heat transfer fluid, we can see that it is the much more efficient heat transfer fluid, since it melts almost all of the PCM at around 30 seconds. However, this is not surprising, since water has a substantially higher heat thermal conductivity and specific heat compared to air. Something to note is that the air-based simulations ended up having a higher liquid fraction than the water-based simulations. And this means that more energy was stored in the form of latent heat. So water is the more efficient heat transfer fluid. Meanwhile, air allows for more energy storage. Yeah.
To assess the influence of flow velocity, we compared 4 simulations, 2 featuring air at 10 meters per second and 2 featuring air at 5 meters per second. And as you can see in this graph, the simulations with air at 10 meters per second outperform the simulations with air at 5 meters per second, both in temperature and in liquid fraction. This is not strange, because the higher flow rate increases convective heat transfer within the heat transfer fluid. However, it is still important to note that the effect of flow velocity was still relatively modest compared to the effects we saw when switching heat transfer fluid from air to water.
And just one point as well. Thank you. And the last parameter we looked at was the heat exchanger configuration. And here we see the contours, the temperature contours with parallel flow. There we go. And here with counterflow. And you see here the temperature is around 325 degrees Kelvin. That is by volume, the average temperature of the inlets. So that's interesting. And as we saw earlier with the graphs, we did reach a steady state. So this part is probably melting since it's at melting temperature. But the situation is, however, quite different when looking at the counterflow heat exchanger. This part is at the hot inlets, and you have the 350 degrees Kelvin, while this part is at 300 degrees Kelvin, which means that this part is rock solid and this part is liquid, therefore storing less heat than the parallel flow heat exchanger.
Now, this study examined the impacts of the 3 variables. However, further studies could still be conducted, and for example, turbulent flow models could instead have been used instead of the laminar flow model, since that would most likely have been more realistic. The geometry of the heat exchanger could also have been altered, for example, widening the PCM tube. And longer simulation runs also have to be conducted in order to simulate real-life scenarios, which often have longer operational periods.
So, in conclusion, this study has investigated the heat transfer characteristics within a PCM-based heat exchanger. We have found that the heat transfer fluid has the greatest overall effect on PCM melting rates and heat transfer within the exchanger. We also found that parallel flow configurations needed both greater and more uniform PCM melting within the exchanger. We have also found that an increase in flow velocity increases both PCM melting and overall temperature difference within the exchanger. These simulations highlight the importance of both heat transfer fluid, heat exchanger configuration, and choosing the right velocity in optimizing PCM-based heat exchangers.
Wonderful. And to close off this presentation, we want to thank Ashna for her patience, kindness, and guidance throughout this project.
We would also like to extend our gratitude to Kungliga Patriotiska and Tage Svan Stiftelse för undervisning och forskning for making this possible.
And last but not least, we would like to thank Race for Excellence for giving us this opportunity to stand on this scene in the Tekniska Museet, and especially thanks to the Race Organizing Group of 2025 for taking care of us and sharing their wisdom.
I'm kind of interested in, have you guys considered removing the incompressibility assumption? Because what you're looking at is something that's basically changing phase. That's a change in density. Doesn't that affect?
Well, that's in the PCM.
Yeah, so I guess you guys aren't looking. I mean, you don't think that would affect the heat transfer characteristics within the PCM?
No, I don't think so. And we didn't mention it here, but the big part of choosing PCM is really a field on itself. It's also you want to not have a change in volume. For example, you don't have water as a PCM for the simple reason that it changes volume. And in this case, it would mean that the compartment in which we have the PCM would kind of explode. So yeah, we don't want that, and therefore we have a pressure-based simulation. Yes.
You mentioned towards the end that possible further studies to use turbulent flow instead of laminar flow. Do you have any idea of like how the results would change, or how off it is to use laminar flow instead of turbulent?
I don't think that results will skyrocket in annually, but it will surely vary and most likely induce more heat transfer in the forms of convection. So it will more likely be a more efficient heat exchanger than what we yeah.
So about that equation.
The
no, I'm kidding. But like, has this ever been tried in practice?
To do what?
Actually try and store energy in this way and you use it to like heat up buildings.
Yes, yeah. We actually saw a heat exchanger in use at KTH. Yeah, there was a nice professor who showed us one, or maybe one. He showed us a lot of things, but an exchanger, yes.
Did they use this model, or like what's the geometry PCM used?
There are different types of geometries. This is a very simplified version because normally heat exchangers are something called shell and tube heat exchangers, where there are a lot of pipes within the heat transfer fluid. So it's quite different, I guess.
Yeah.
Did that answer?
So.
And like the phase change material, do you know which one they used, or?
He used in this professor.
No, like at KTH.
Yeah.
Their actual, or was this?
No, they didn't use an IPC, right?
They were testing several different ones, but one of them was the sweetener in drinks that says no sugar. The sweetener used was one of the PCMs.
Yeah.
So, and it's pretty much looked like sugar, but I guess no sugar. So, yeah.
Yes.
How many times did you run the simulations?
How many times we run the simulations?
Yeah.
Well, they take quite a lot of time, so each simulation was just once.
Okay.
Yeah. Any more question? Yes.
How long did the simulation take?
Well, it varied from.
It ranges anywhere from 2 hours to 15 hours, I'd say.
Yeah.
Yeah. One question? Yeah.
In what language was the simulation done? In like what programming language or?
The simulation was done in the like CFD software as a student.
Okay.
So we didn't program.
Okay.
Thank you.
Thank you.
Thank you so much. Now it's time for Gustav Bondensson to enter the stage. Gustav is a student at the Natural Sciences program at Gymnasiet in Falu with a strong interest in astronomy and material science. He has taken part in numerous competitions and camps in physics, chemistry, and mathematics, and is the co-founder of Gil Estel, a local astronomy association for youth. Alongside his academic pursuits, Gustav is active in scouting, choir, singing, and piano, and has received several music scholarships. At KTH, Gustav worked under the guidance of Professor Christopher Durig and Aulasan Ahmed. Give a warm applause for Gustav.
As you are all surely painfully aware of, our planet is getting warmer. The glaciers are melting, our seas are getting higher, and it's our fault. You can hear me. No, that's not good. Hello? Oh, that's better. All right, now I'll redo the thing. But the climate, it's getting hotter. Our planet is getting hotter, and yeah, those changes are not going to go unnoticed. The Potsdam Institute for Climate Impact Research detailed in a study published last year in Nature the consequences of unmitigated climate change. They actually stated that we have already committed future generations to well, some pretty severe economic burdens. How great these burdens grow, well, it depends on how quickly and how well we act now. But there are already many millions of people whose, well, their creative potential, it might be lost because their time and energy is going to be pointed towards solving the mess we made instead of, I don't know, curing cancer or building rockets. Quite sad. Another thing, however, that they outlined is that the cost of mitigating climate change today is several times less the costs that are going to be forced upon us should we fail to act now, but these costs, of course, do not come now. Pollution is expensive, just not going to do the polluting. The problem. And here in Sweden, we are, of course, very proud of our mitigations when it comes to climate change. We don't burn a lot of coal, but there are other industries which are a bit harder to make climate neutral, especially our steel and concrete industries. What is good, however, with these industries are that they are more or less very centralized industrial processes. You have one big smokestack emitting the carbon dioxide, which means point source carbon dioxide capture is an option. That means that you have your smokestack, you have your gases, and some of those gases are carbon dioxide, you manage to separate them from the rest of the gases, you compact them, you transport them away, and you sequester them beneath the earth. Of course, you would have to separate the gases, which may be done by capturing the gases into some kind of liquid solution. What exactly the solution should be, well, the researchers aren't really in agreement. There's some different avenues being tested. However, regardless of what your solution is going to be, contact area between the gas phase and the liquid phase is crucial. You want as many places as possible where this mass transfer can occur, and which is why we utilize packed columns. It's kind of a smokestack with a packed bed in the middle. A packed bed, it's a kind of structure that has a very high surface area per volume. So what you can do is you pour down your chosen solvent above the structure. It, at least in theory, coats every little nook and cranny of your structure, giving it and of course you can take your gas from below and you get this environment where there's a very high amount of surface area between phases, and the carbon dioxide can be efficiently captured from the gas into the solvent, which may then be scrubbed and reused. However, these structured packings aren't very effective. They're easy to manufacture, but there are potential for improvements. And through the advent of additive manufacturing, also known as 3D printing, well, new opportunities present themselves. Among these new structures are a group called triply periodic minimal surfaces. These structures are found naturally occurring in nature, actually in the wings of butterflies, but they also have some pretty strict mathematical definitions. They're pretty neat. I recommend checking them out. But what's important for our purposes is these structures have very smooth and labyrinthine paths divided into the structure, meaning, well, not meaning, but they do distribute stress and, in our case, liquids quite nicely. And said and done, we decided to manufacture a couple of experimental structured packings using some different TPMS structures. Among them were the primitive lattice variant, the gyroid lattice, the diamond lattice, and the gyroid solid. And all of these structures, which are essentially, you have a volume and you divide into two distinct regions, depending on which region you decide to print, because reprinting, and you get two different variants. So every structure has two sides of the same coin. These structures were printed using stereolithography. It's a kind of fancy 3D printing. You use a kind of ink instead of plastic. It's smooth. And this is the solid gyroid. And these experimental structured packings were then fitted inside a setup simulating the conditions of a packed column. As you can see, we had a reservoir filled with water because these solutions are usually water-based, which could be pumped through the pump and introduced into the column via a configurable inlet. and it was then poured down through the structure, and when it exited beneath, it was captured by a segmented liquid collector. This segmented liquid collector had each segment drained to a specific bottle, meaning we could know how much water was exiting the structure at different parts of it. And this allowed us to create a kind of map about concerning how the liquid or the water is distributed within the structure. Using a earlier established equation, you can get a single number called a maldistribution factor, which just quantifies how evenly or unevenly the water is distributed, and the lower the value, the better or more uniformly. As you can see, this is as you can see, this is the segmentation of the liquid collector, and this is how it looks in actuality. Unfortunately, when we compared the different structures, we did not manage to do a lot of experiments, so our uncertainties are quite high. There was also a lot of variability between experiments, but nonetheless, we managed to find that the solid gyroids seem to perform not as good as its lattice variant when it came to just the general maldistribution. We also decided to investigate how the inlet conditions impacted the distribution within the structure. We placed a perforated 3D printed grate, a bit like the one you find in the shower, between the nozzles and the structure to try to disperse the liquid a bit more. We also tried using only one nozzle instead of 5. As you know, I'll show some diagrams soon. As you can see, well, we can tell actually how we did it. We did 2 experiments, first one with the grate and one without, and then we quantified how big percentage each section constituted of the whole liquid that flowed through the column, and we checked the difference with the grate and without the grate. And here we see that when compared to the grateless structures, and these are all the same structure, one structure, another structure, we had a lot more water in the outer edges when we used the grate. This is true for both the gyroid solid and the gyroid lattice. When we instead only used one nozzle instead of 5 nozzles, we got a lot more concentration in the middle, which however, there were some pretty clear systematic errors, unfortunately. As you can see on the primitive lattice here, between the grate and we did not have the grate, there seems to be a strong aversion of the water of this quadrant. It's quite possible this had nothing to do at all with the grate. What's rather quite likely is we misaligned the column between the experiments, and we tilted it a bit in one direction, so it wasn't perfectly straight, and then water is flowing in different paths. But it's nothing to do with the grate. There's also the problem of water having quite a high surface tension, which means it likes to clump together. So it could be pretty evenly and easily distributed within the structure, but once it exits underneath, it converges and creates a bunch of few and pretty large streams. And some of these streams might just happen to drop into one collector or the other, showing these very lopsided collector data. As you can see, there's quite a gap between the structure and the collector segment. So that's an issue. Nonetheless, we could conclude that the solid gyroid underperformed compared to its lattice counterpart, and is probably not very suitable as structured packing. And we also concluded that the inlet conditions do matter for the distribution. And it's how the distribution is in the bottom of the column is affected on the inlet conditions. I wish to thank, of course, my mentors, Professor Christoph Juli and Dr. Hassan. Their guidance has been most appreciated. Of course, I must thank our organizers and our Race for Excellence collaborators who made this possible. Do we have any questions?
So obviously using gas and water are pretty different. So what are some challenges you foresee in developing this kind of method for gas?
Well, they do these in spray towers where they have like, you have to have it sealed. Or do you mean like experimentally or actually in, you know, in real packed columns?
Both really.
First of all, when you do it experimentally, it's, well, you have to have a lot more sensors. You have to have really, really tight. Industrially, I mean, there's the problem of pressure drop, which I guess you can't really optimize for when you do these experiments because we only try to get as even a distribution as possible. But another factor that's very important when you actually use gas is you don't want the gas to get slowed down too much, which I guess could mean the results you gain by only testing for liquid distribution might be misleading because you might optimize for even distribution and maybe you could land at very small pore sizes. But then when testing this in actuality with gases, you can find that, oopsie, the gas is slowed down too much.
Thanks.
Yes.
But like, how would you account for that?
So you mean how would you account for that?
Like the difference between the experiment trying it on purely liquids and then in actuality having it function for gases.
Well, I mean, you can do experiments and simulations, safety simulations with both gases and other sort of multiplayer phase experiments.
Was there any reason?
I guess this is more honest.
Was there any reason for why you didn't do it in this experiment?
Well, it's a bit more time sensitive. You can't really do as many experiments. Besides, this is more efficient if you just want to down select the structures. For example, it would have been extremely inefficient to be testing multi-phase flow with the solid gyroid since it proved to be pretty useless. So I mean, this process is more just finding like the easiest filter to kind of skim away the largest amounts of rubbish, and then we can refine it with more refined methods. Yes.
Could you compare the structures for efficiency, which is the most efficient in terms of your absorption?
No, well, due to safety concerns, I was not allowed to use any kind of solutions that absorb the carbon dioxide because they had some, well, caveats with the caveats. So I couldn't do such experiments. Is that all questions answered? I think so.
All right. Now, it has become time for the last presentation of the day, which will be given by Arvid Saranoa, Linnea Sten, and Melody Young. Arvid studies the Natural Sciences program at Norra Real in Stockholm. With a strong interest in aircrafts, particle physics, and astronomy, Arvid has participated in numerous science competitions and camps. He is also actively involved in Astronomisk Ungdom, where he serves as a project leader for this year's National Astronomy Camp. In his free time, Arvid enjoys stargazing and photography. Linnea studies the Natural Sciences program at Presentation in Helsingborg. He has a deep passion for physics, mathematics, and astronomy, with a particular fascination for dark matter and black holes. Linnea is active in Girls in STEM, writes for the youth science magazine Particular, and serves as a communication officer for UVS Fysiker. In her spare time, she enjoys orienteering, both as an athlete and a coach. Melody is entering a final year of the Natural Sciences program at Presentation in Helsingborg. She has a strong passion for mathematics and astronomy, and she's attended several science camps and is engaged in youth organizations focused on science outreach. Melody helps found a science committee at her school and has a background in competitive volleyball. During their research project at KTH, Arvid, Linnea, and Melody worked under the guidance of Professor Jean-Pierre and Dr. Priyanka Shodari. Give a warm applause to the group.
Can you hear me? Yes. Thank you for the introduction. My name is Melody, and with me I have Linnea and Arvid.
We have focused on investigating 3 different nucleosynthesis processes in core collapse supernovae. I have focused on the neutrino process, Linnea has focused on the gamma process, and Alvin has focused on the neutrino-driven arc process. So to begin with some introduction to the core collapse. Stellar fusion in massive stars stops when it reaches iron group elements, at which point the core starts to contract under gravity. This increases the density and temperatures, and it allows for electrons to get captured by protons and free nuclei, creating neutrinos. But this decreases the pressure from electrons, which makes it so that the core can no longer support itself against the gravity, and thus it starts to collapse rapidly. However, the collapse is also very abruptly halted, as the density and pressure becomes so strong that the core is instead pushed outwards, creating a shock wave of energy in the form of neutrinos. And this shock wave is known as the core collapse supernova.
So the simulation we used used stellar models from Mesa, Woolsey, and Mueller. These stellar models were the progenitor models for the actual stars that explode in supernovae. It simulates the entire process from beginning to end in the 2 dimensions and calculates the physical quantities that we get from that supernova. And it also determines if the result is a black hole or a supernova and its eventual pre-neutron star and neutron star.
So I studied the gamma process, which is one of the processes under the umbrella term of pre-processes, which is the nucleosynthesis of the so-called p-nuclei, which are proton-rich, rare isotopes that can only be formed during core collapse supernovae. And the studying the gamma process is crucial in the knowledge of how and when these p-nuclei are synthesized in the universe. And the gamma process is a chain reaction of photodisintegration reactions, where gamma rays, which are photons with high energy, are exciting a nucleus and by that emitting a particle. And there are 3 types of nuclear reactions: one where a neutron is emitted, one where a proton is emitted, and one where an alpha particle is emitted. And for the gamma process to occur, there need to be some optimal conditions. The temperature has to be between 2 to 3.5 gigakelvin, and the gamma process is often occurring in the neon or oxygen layer of the star within the time frame of 0.1 to 10 seconds after the core collapse supernova. And the higher temperatures in the range for the gamma process are more efficient for the synthesis of the lighter p-nuclei, whereas the heavier p-nuclei are synthesized in the lower temperatures due to the photons due to high energy by the photons will not make the heavier isotopes stable anymore. And in previous studies, the overproduction factor has been used to study the gamma process. And it's used as an approximation for the production efficiency for a certain isotope, where if you don't have the data for the p-nuclei itself. And core collapse supernovae are known for being huge producers of oxygen-16, which is an isotope that isn't directly affected by the gamma process and could therefore be used as an approximation for the gamma process. And it's calculated by taking the mass fraction of the ejecta from the supernova and dividing it by the solar mass fraction, and then taking the ratio between the p-nuclei's overproduction factor with the overproduction factor for oxygen-16 to get a ratio of how efficient the production of the p-nuclei was in the stellar model. And a ratio of about 1 indicates that the gamma process was efficient in this stellar model. But however, previous studies have shown that the gamma process is ineffective in most of the models, so a ratio of 0.5 has been accepted as the standard value. And the method used for this study was analysis of Mesa data for a 15 solar masses binary star and calculating the overproduction factor of oxygen-16 and then comparing it to the overproduction factor for a range of p-nuclei in 4 different stellar modules due to the MESA data lacking information about the nuclei. And the optimal zones for the gamma process was also tracked in this stellar model to make sure that the gamma process was actually occurring by tracking the optimal conditions against the radius of the star. And here are the results for the overproduction factors, where we can see that for one of the models, the lighter p nuclei seems to be produced more efficiently. However, looking at all of them, we can see that there is a slight increasement for the efficiency of the heavier nuclei. But if we look at the ratio overall, we can see that it's quite low, which indicates that the gamma process may not be that efficient in this stellar model. And here we have the results for tracking the optimal zones for the gamma process, where we can see that the optimal temperature and here is the mass fraction for oxygen and neon against the radius. And we can see that the spike in the mass fraction is in the same place at the radius as the optimal temperature, which indicates that the gamma process was probably occurring in this stellar model. And here we have the time frame as well, up to 10 seconds. And here we can see that this is where the gamma process occurs. And we can see that the temperature is not reaching the highest it could, which indicates that the lighter p nuclei may not be produced as efficient as the heavier ones in this model. So to conclude, there was a low production of p nuclei in comparison to oxygen-16. However, we can confirm that the gamma process was actually occurring here, as all the optimal conditions seemed to be in the same area of the star. And both the overproduction factor and the optimal conditions confirms that the heavier p nuclei were produced more efficiently than the lighter ones. But an error source to take into consideration is that they were only researching one stellar model due to most of them turning into black holes rather than neutron stars, as well as it was hard finding data of the p nuclei overproduction factor, which is something that could be studied further.
All right, so you can hear me, right? There's nothing wrong with the sound. Good. Well, in these exciting high-temperature, high-density environments, like supernovae, we have 3 processes that occur in a sort of path that we'll see later. It's neutron absorption, oh, you have to hold it, where the nucleus absorbs a neutron, because neutron just float freely in supernovae, and they then have to emit gamma radiation to get rid of that energy. The reverse of this, which Linnea talked about earlier, a version of the photodisintegration, and when those isotopes get to unstable, beta minus decay, where it then just switches nuclei, where one neutron turns into a proton and electron and makes the nuclei emit an electron antineutrino. This is what that path looks like, the neutron absorption and photodisintegration working against each other until they find some sort of equilibrium, where it will then stand and wait for a while until it goes through beta minus decay, doing the same thing again. This sort of path is along a plane called the proton number, neutron number plane, where we can see all the natural stable isotopes in what is called the valley of stability. Now, there are 2 sorts of neutron capture processes. One is called S process, slow neutron capture, where it goes it absorbs a neutron, it goes through beta decay, kind of just does that, and it doesn't produce that many heavy elements, but that a lot of heavier elements. And the rapid neutron capture, where there is rapid neutron absorption, and it just goes kind of wild, and it makes those heavier elements. But these elements often just reach what's called the neutron drip line, where it cannot absorb any more neutrons, and just goes through a series of beta decays until it reaches that first stable isotope in the valley of stability. But this is not a normal case. This is what is called the neutrino-driven R process, where neutrino absorption has the kind of same effect on the nuclei as the beta decay, except that the isotope doesn't have to emit any antineutrino. And This leads to the previously mentioned p nuclei through the beta decay effect being added onto. It does not stop at that first stable isotope. It pushes beyond and reaches these, as Leanne talked about earlier, proton-rich, naturally occurring isotopes. But where do we find these? Where are they actually in our universe? Well, there are 5 conditions that I looked at, which give the favorable condition for neutrino-driven R process, which is temperature, density, entropy per baryon, electron fraction, which is entropy per baryon. It's entropy per neutron and proton. Electron fraction, how many electrons per proton and neutron, and neutrino exposure, how many neutrinos basically. All these conditions can be found in 2 places, supernovae and neutron star mergers. Neutron star mergers are when 2 neutron stars merge. It's kind of simple actually. There's one previous study done on this process from last year called Zhang et al. They are the ones that proposed the process, and they used what is called parametric trajectories, where they assumed perfect trajectories for the neutrino-driven R process to happen. These exact conditions are to your side, and to reach these, you have to choose a star, progenitor star, with a lower metallicity and lower mass while still being above 8 solar masses, which will eventually result in a pre-neutron star with a mass of 1.2 to 2 solar masses. And, all right, well, I kind of did that wrong, but the neutrino exposure proxy is a proxy that has to be used, because neutrino exposure, as seen earlier there, you can't get that from supernova simulations. So you have to use some approximate value. That's the proxy. It uses expansion timescale and neutrino density instead of expansion timescale and neutrino capture rate. The aim of this study is to see if a successful neutrino-driven R process can be realized in supernovae and compare previous use of trajectories that were kind of perfect to the simulations that we can simulate ourselves, and to finally determine the role that neutrino-driven R process and R processes play in the production of P nuclei. We ran the simulation code, as said earlier, with the Woozley format files. We chose a star with 12 solar masses and a metallicity that is 10 to the power -4 of the one of our local star. And we had to determine the mass of the neutrino-driven winds, because that is between the actual pre-neutron star and the ejected mass of the supernova. The neutrino-driven winds are, and that's where the neutrino-driven R process happens. And after that, we had to put it into the mass coordinates, see what do we have for electron fraction, what do we have for temperature, now that we know electron fraction, and again with all the other graphs. And the results were that we got a mass of the pre-neutron star to 1.39 solar masses, the neutrino-driven winds were 0.4. So adding those together, since mass coordinates go from the core outwards, we get that the neutrino-driven winds are between 1.39 and 1.79 solar masses, which we can see in this graph for electron fraction. That value, which is supposed to be between 0.4 and 0.5, is between 0.4 and 0.5. And the temperature almost reaches the desired value of 10 to the power 10 in that electron fraction. And the density is also very favorable, between 10 to the power 6 and 10 to the power 8. The entropy, on the other hand, is 3 or 4, between 3 and 5. It is supposed to be 84. And the electron fraction that we have says that the neutrino exposure in the supernova only reaches 10 to the power 31 instead of 3.34 times 10 to the power 33. These values you can see here, or read in my report if you want to know them. So we got a favorable density, we got a favorable temperature, we got a favorable electron fraction. We did not get a favorable neutrino exposure proxy, and we got an extremely unfavorable entropy per baryon, actually being 80% less than what we wanted. A source of error for this can, of course, be that we approximated the neutrino exposure, but that does not disregard the extremely low entropy per baryon. So I still conclude that neutrino-driven R process is extremely unlikely to occur in supernovae, maybe specifically this supernova, but with material introduced in the beginning, it seems unlikely in all supernovae, which is actually a thing that people have said before, because a normal R process has its main source in neutrino or neutron star mergers. And therefore, to reach the higher entropy per baryon and the higher neutrino exposure, the more likely candidate is this neutron star merger.
Yes, now on to the neutrino process. So the neutrinos that were released with the supernova shockwave play a big role in the nucleosynthesis of some rare isotopes whose origin cannot be explained through the SR or gamma process, and instead can be explained through the neutrino process. And one such isotope is fluorine-19, which I have decided to focus on for my study. So the aim of my study was to investigate the likelihood of the neutrino process being a main contributor to the fluorine-19 abundance that can be observed. And it's based on this neutron current reaction here, where a neutrino knocks a proton out of a neon-20 nucleus, resulting in fluorine-19. And as you just saw in the reaction I showed, in order for the neutrino process to create fluorine-19, we need a high abundance of neon-20. We also need a lot of neutrinos, and therefore a high neutrino luminosity. The timing also needs to be considered, as the neutrino process needs to occur before the neon-rich shells of the star are altered or destroyed by the shockwave. Temperature, density, and entropy have also been found in previous studies to affect the neutrino process, and these values that are shown here have been found in previous studies to be the most optimal conditions. So the method I used was that I took stellar models from MESA and ran them through the simulation that we mentioned in the introduction to determine which ones ended up as black holes and which ones ended up as supernovae. This gave me a range of stars from 10.99 to 16 solar masses, as these ones ended up as supernovae, which is relevant for my study. I then gathered the relevant quantities that were calculated also in the simulation and plotted the relevant data on several graphs. Here we can see the neon-20 abundance across the stellar layers, and by studying it, we can see that in the mass coordinate range of 1.5 to 2.5 solar masses, neon-20 abundance is the highest and remains high. This corresponds to the neon-rich shells of the stars. We can also see that these neon-rich shells are more extended in stars of higher initial mass, which could suggest that there is a higher or bigger area where the neutrino process could occur. Here we can see the neutrino luminosity over time, which shows a neutrino luminosity peak at around 100 milliseconds after the shockwave. The following results that I'm showing now were all studied within the neon-rich shell's mass coordinate range, as this is a relevant area where fluorine-19 can be created. And so I found that temperature and entropy were within the optimal range that I mentioned earlier. The density was mostly within the optimal range, except for some stars, or for the stars with lower initial masses, as these showed that the density dropped below the optimal value within the neon-rich shells. And lastly, the infall time was much higher than 100 milliseconds for the whole mass coordinate range for the neon-rich shells, which indicates that these shells are still intact during the luminosity peak and therefore exposed to a lot of neutrinos. So what I can conclude from my study is that neon-rich shells were exposed to a strong neutrino fluence, enough to possibly let the neutrino process occur. I also found that the other quantities aligned well with what was previously found to be the optimal conditions for the neutrino process. And lastly, I found that pre-supernova stars with higher initial mass may actually offer better conditions than those with lower mass, as they showed extended neon-20 shells and more optimal density conditions. And now to some further studies that we all would like to work on together in the future. To begin with, as this was a very short time frame, we did not have the time during this project to work on more complicated nucleosynthesis programs such as Skynet, which would allow us to
make more precise analysis and focus on specific different parameters.
All right. We would like to extend our highest gratitude to our mentors, Priyanka Chuderi, who's sitting right there, and to Professor Chang-Chi, and to our Race for Excellence partners, Stiftelsen and Kungliga Patriotiska Sällskapet, for making this possible.
Do you have any questions?
I'm really curious, why is entropy so much lower in supernovae compared to neutron star mergers?
Oh, well, that is a really good question. I have no idea why, actually, I'm going to be honest. I would like to be honest with this and just say that I have done research about what would be the more likely candidate, and since our process doesn't actually mainly come from supernovae, but actually does mainly come from neutron star mergers, because a team of scientists in 2017, I think as anyone astronomy interested would know, saw a neutron star merger, and then like everyone across the globe measured it, and in these measurements they found that while sufficient R process material was not found in supernovae, which was a previous concern, it was found in these neutron star mergers and their ejecta, and therefore I concluded that if that is the more likely place for our process to happen, since these the results I came to actually didn't even warrant a successful R process because the entropy per variant was not high enough. So I thought that, yeah, maybe neutron star mergers, the actual main source for these for this R process, would be a better place to search for the neutrino-driven R process.
More general question. What are some factors that cause a star to become either a black hole or a core collapse supernova? So no mass was alluded to before, so are there any other factors?
Good question.
It's mass and metallicity, isn't it?
Yeah,
And like if it's a binary or
Exactly.
yeah. So the simulation takes into account all of these factors, and it can be found in a report. So if you want to read more about it, there you can find it.
But generally, of course, the mass, but the metallicity also leads to they kind of play together and see, well, how intense is the supernova, and that kind of gives if the density and temperature is high enough.
But one thing I also didn't mention here, because we had to shorten down the presentation a bit, was that during the core collapse, what first occurs during the initial shockwave is the core bounce, and then the shockwave can actually be stalled, and if it is revived again, is what determines if it ends up as a black hole or a supernova. And this, what determines if the shockwave is revived is if the neutrino heating is effective enough to heat the surrounding matter in order for it to get energy that exceeds the gravitational energy.
Thanks.
Any more questions? Thank you.
Thank you, Arvid, Linnea, and Melody. I'm so proud of you all. Now we've finished the presentations. What a day! It's been going. We will have a break now, but we will move it, so we will have it it until 15:30, so 10 minutes earlier than in the schedule. So take some time. See you soon.
Det var 40% på alla avsnitt. Ja, har du skickat det?
Ja, det var ju. Man hade ju kunnat få allt Yes. Oh no. Det var det varit hela dagen, så jag var rätt vågat. Om ingen märkte det så är det. Jag trodde det bara var lågupplösning. Det är bara att ta bort avlastning. Men så här, it's fine, don't worry. Ultra 4K. Yeah. Skulle snacka vid cool.
All right, welcome back everyone. This has been a wonderful, wonderful day. I'm super proud of each and every one of you. And I have many things to say, but I'm not really sure how to say them. This is a day of celebration, not only of academic accomplishments, but also the time we've spent together and all of the things we've done and all the fun things and all the difficult things and everything we've gone through and as a group. And I'm just so proud of each and every one of you. So I have some pictures I want to show you. Yes, of our time. Yes, of our time from Tekniska. We'll start strong. This was the first week when we celebrated midsummer together. It was very sunny this day. We had great weather. We built a midsummer bowl from scratch. We went to Big Macs and got the planks, and then we built it and we found all the flowers and made stuff. We had some dances and we made a lot of food. So this was a great day. We've also directly after this day, we went on a hike and we went on canoes. So we went 4 hours on canoe, and we had great weather. It was sunny. We had a lot of nice talks about fire. We made some roasted marshmallows, and we spent the night in the woods. It was not very good sleep for me, but it was a lot of fun. Then we also brought the Olympics to race. So we in our groups here competed with challenges and puzzles, and it was a lot of fun. And yeah, Erik looks very happy on that picture when you won that challenge. Then we've also worked on our projects, of course. Here we have some guest lecturers first. So we welcome Magnus Ehinger to camp. I was starstruck too. It was a lot of fun. And then, of course, Aija presented, yes, and Louise and Benjamin as well. So we had many different researchers coming here. It was a lot of fun. And we went to visit AstraZeneca in Södertälje as well, their production site. It was a lot of fun. And that picture is not on Instagram because you guys asked about that. So it's in here instead. And then we have worked on our projects quite a lot. Here we have some pictures from both when we're in the lab, but also when we're working on our reports, reading and writing, sitting on tables. Oh, it was a lot of fun. And we also have pictures from when we in the organizing group visited the labs. Here we have some different ones. So, yeah, I think you recognize the groups here. It was a lot of fun for us to see you working in practice during the week. And because we missed you during the days when you were away. So this was a highlight during our time there. Then, of course, we had a celebration 2 days ago when we turned in our reports, our final reports. And it was a lot of fun. I was incredibly proud, and I'm still incredibly proud, or even prouder today because of everything we've seen today and everything you've accomplished during such a short amount of time. I don't think we all understand how much we've done in such a short amount of time. It's crazy. It's been a month, but it's felt like a half a year at least for me. And it's been so much fun. And I think this is the final pictures that I have put in the slide. Let me see. No, we have more. This is from our bed shakes. So every day at the evening we have bed shakes. And that's when we in the organizing groups meet and talk about the day and how it's been and what's been good and what's been not so good, and talk about how to come through. And yeah, it's the sad thing about being a project director or the director of RACE is that I don't get to have these meetings with the students because I don't have an organizing group. But that makes it so much fun to go and talk to each and every one of the groups when you have meetings. So that's been definitely a highlight of my month. So these were the pictures from the first week, and there's my organizing team on Midsummer. So yeah, it's been something this month. It's been so much fun. I think this is the last slide, I think. Yes, that was the last slide. So thank you all students. Thank you so much. And now it's time for diplomas. So I welcome Selma up to stage. Do you want to have this microphone? Yes.
Får jag sitta här?
Okay, I will now read your names one by one, and then you will come up here, get your diploma, shake Hannah's hand, get a picture from Victor, and then you can stay on the stage until, in line here, until everyone has gotten their diplomas. So the first person I want to welcome up on stage is Linnea Sten. The next person is Summer. Eugene Young. Eriksson. Dante Wigren. Yishu Zhang. Nico Kai. Anissa Jafari. Paulina Blom. Melody Jung. Gustav Bergin. Gabriel Textoris. Isabel Linder. Gustav Bondesson. Anastasia Sarashina. tack Eleverna, kör ni.
Nu ska vi då göra det omöjliga. Vi ska ta en grupp. Jag vill att ni ställer er centrerat på scenen.
Nej, det ser inte.
Vad fint. Okej. Albert, kan du flytta in bakom där precis? Och sen kan vi allihopa ta ett steg ditåt. Snyggt, då börjar det likna något. Okej. Och så, vad ska vi säga på 3? Oh my race. Okej. Så 1, 2, 3.
Oh my race!
Nice. Ska vi... Det kan vi göra. Ta typ den första. Där, ja. Alright. Då har vi övat. Då är det på riktigt. Så då kör vi på 1, 2, 3.
Oh my race!
Nice. Tror du att vi kan få med arrangörsgruppen också?
Om jag tar bilden?
Ja.
Ja.
Det är bara fokus. Alla håller i fokus. Det här är kanske så precis att vi ser det lite bakåt. Okej.
Det är galant. Ja, det ser bra ut. Ja, men vi kör på 3 igen. 1, 2, 3.
Oh my race!
Ja, vi kör en gång till. 1, 2, 3.
Oh my race!
Ja, något sånt där kanske. Ja, super.
Stort tack till alla som har kommit idag. Det har betytt jättemycket. Och jag är så stolt i er. Tack så mycket!